Welcome, friend, to this quiet space. Take a gentle, deep breath. Where are you right now? Perhaps you are nestled in a soft bed, the light dim and soothing. Or maybe you are sitting by a window, watching the serene darkness descend. Wherever you are, at whatever moment, please know that this is a space created just for you. A space free from pressure, from the need for instant answers, from any rush. This is not a lecture, nor is it therapeutic advice. Simply, it is a whisper, an invitation for your mind to wander through the most wondrous concepts of the universe, of science, of the mysteries we are still gently uncovering. We will journey together, not on star-dashing spacecraft, but through the quiet expanse of our own imagination. We will touch upon grand ideas, questions that have no complete answers, and you will find, within that immensity, a surprising stillness. Allow the thoughts of your day to dissolve like tiny dust motes in the setting sun. Permit your curiosity to lead you softly, without urgency, without compulsion, just exploration, in the most tranquil and peaceful way imaginable. In this journey, we will not seek absolute certainty. Science, at times, is like walking through a mist, with only a faint light as our companion. We perceive vague shapes, feel strange breezes, and sometimes we can only wonder what lies hidden ahead. Is it daunting, or is it another kind of beauty? A new secret waiting to be unveiled. Let your mind float, drifting with these streams of thought. There is no need to actively remember, no need to analyze, just feel. Just allow these grand ideas to gently envelop you like a warm blanket of wonder. We will explore the stories the universe whispers to us, tales of strange visitors from deep space, of enigmatic phenomena right here on our own planet, and of humanity's ceaseless quest to understand its place in the magnificent tapestry of existence. This is not medical advice and is not intended to replace professional therapy or medical consultation. Its sole purpose is to provide a calm and reflective space for exploration. Have you ever considered the possibility of a message from the stars, not in words or coded signals, but in the very presence of an object, a silent, fleeting visitor? The universe, in its boundless generosity, delivered such a messenger to our solar system, a peculiar wanderer named Oumuamua. Its name, a beautiful Hawaiian term meaning scout or first distant messenger, truly captures its essence as the very first interstellar object we ever recognized. It glided into our cosmic neighborhood on October 19th, 2017, a small, unassuming speck of cosmic dust and rock that would soon ignite a fiery debate among scientists, a debate that continues to whisper through the academic halls even today. When it was first glimpsed by the Pan-STARRS telescope high atop Hawaii's Haleakala volcano, scientists almost immediately sensed something unusual about it. Its estimated size, somewhere between a mere 100 and 1,000 meters long, was not what drew their intense focus, nor was its seemingly peculiar shape, thought to be either an elongated cigar or a flat, pancake-like disc. This unusual form was inferred from the way its brightness fluctuated as it tumbled through space. If it were perfectly spherical, its light would remain constant, but its irregular rotation caused it to brighten and dim rhythmically, suggesting an oblong or flattened profile, much like a leaf twirling in a gentle breeze. But the true source of Oumuamua's enduring enigma, the trait that catapulted it from a mere astronomical curiosity to a profound scientific puzzle, was its motion. After gracefully looping around our sun, Oumuamua began its slow, deliberate journey back out of our solar system. And as it did, it started to accelerate. Not in a dramatic, sudden burst, but with a subtle, persistent push. This acceleration was minuscule, a mere 17 meters per second when it was closest to the sun. yet it was enough to send ripples of bewilderment through the scientific community. Oumuamua was simply not behaving as the laws of physics, as we understood them for celestial mechanics, dictated it should. Think about it for a moment. In the vast, silent arena of space, objects move under the precise, predictable influence of gravity. A planet orbits a star. A comet sweeps through the outer reaches, all following paths that can be charted with exquisite precision. If something deviates from that path, if it unexpectedly speeds up or changes direction, it implies that an unseen force, a non-gravitational push, must be at play. This fundamental principle is as clear as a ripple spreading across a calm pond when a stone is dropped. Something had to be pushing Oumuamua. The question then became, what could that force possibly be? Initial hypotheses, the simplest and most conventional explanations, were quickly considered and, just as quickly, discarded. One might imagine the gentle nudge of solar winds, the stream of charged particles constantly emanating from our sun. Indeed, we know that these solar winds can exert a minute force on space objects, a faint breath pushing through the void. Yet, for an object the size of Oumuamua, even at its closest approach to our star, this subtle force was utterly insufficient to account for the observed acceleration. It would be like trying to move a mighty ocean liner with a single gust of wind from a child's toy fan. The scale of the force simply did not match the effect. So, if not solar winds, and assuming it was just an ordinary asteroid, an assumption scientists had to make, given that even the best images were nothing more than a tiny speck of light, making its precise appearance a matter of inference rather than direct observation, then what? Scientists then turned their attention to another class of celestial objects known for their non-gravitational acceleration comets. Picture a comet, a magnificent dirty snowball of ice and dust on its long elliptical journey. As a comet draws near the warmth of the sun, the frozen gases and water ice within its core begin to sublimate, transforming directly from solid to gas. This outflow of gas and dust forms the comet's ethereal tail, a luminous streamer stretching for millions of miles. But this beautiful spectacle is more than just a visual treat. The escaping gas acts like tiny natural thrusters, providing a continuous gentle push that subtly alters the comet's trajectory, accelerating it away from the sun. This phenomenon is well understood, observed countless times, and perfectly explained by the physics of outgassing. However, Oumuamua presented a puzzling absence. Despite its inexplicable acceleration, scientists could detect no signs of such outgassing. They aimed their most powerful telescopes, scrutinizing it for any hint of a dusty coma, any wisps of gas, any indication of a tail. But there was nothing. No hazy shroud, no trail of escaping material. Oumuamua remained stark, seemingly inert, a bare, dark rock gliding silently through the void, completely unlike the bustling activity of a typical comet. This lack of a visible coma, this quiet defiance of expectation, intensified the mystery. If it was accelerating, yet showing no signs of the physical processes we know cause such acceleration in comets, then what hidden engine was propelling it? This profound absence opened the door to more exotic theories, concepts that pushed the boundaries of conventional thinking. Let us now gently enter the fascinating arena of academic debate, where two prominent theorists with vastly different perspectives attempted to unravel Oumuamua's perplexing behavior. On one side, we find Harvard professor Avi Loeb. His theories often capture headlines and stir vigorous discussion. In 2018, Professor Loeb put forth a provocative argument: solar winds could indeed provide the observed acceleration of Oumuamua, but only if the object was far, far thinner than initial assumptions suggested. He calculated that for this to be possible, Oumuamua would have to be incredibly delicate, perhaps only 0.3 to 0.9 millimeters thick. Imagine an object up to 1,000 meters long, yet as thin as a single sheet of paper, or even finer. Such an extreme aspect ratio, Professor Loeb contended, was highly unlikely to arise naturally in the cosmos. If not natural, then it must be artificial. Professor Loeb boldly proposed that Oumuamua could represent alien technology, specifically a light sail, a craft designed to harness the gentle pressure of starlight or solar winds for propulsion across interstellar distances. This theory, both thrilling and audacious, immediately captured public imagination and sparked intense scientific scrutiny. It painted a picture of advanced extraterrestrial civilizations, perhaps sending reconnaissance probes across the galaxy. With Oumuamua merely one such artifact, an accidental visitor to our cosmic doorstep, Professor Loeb, with his considerable reputation and unwavering conviction, ensured this hypothesis remained at the forefront of the discussion. Yet, in the rigorous world of science, new ideas must withstand the crucible of peer review and counter-argument. Professor Loeb's theory met significant resistance from other members of the academic community. Among them was Darrell Seligman, then a postdoctoral researcher at Cornell University. In 2020, Seligman, co-authoring a paper, offered an alternative explanation, one that, while perhaps less sensational, was still quite compelling and sought to keep Oumuamua within the realm of natural phenomena. Seligman posited that perhaps the reason no outgassing was detected from Oumuamua was because the object was emitting an invisible gas, a gas that current telescopes were simply not equipped to detect. His initial candidate for this elusive gas was hydrogen. Hydrogen, being the most abundant element in the universe, seemed a plausible constituent. If Oumuamua were largely composed of frozen hydrogen, a hydrogen iceberg, its sublimation under the sun's warmth could generate the necessary thrust without producing visible dust or light in the wavelengths we observed. Professor Loeb, ever the keen debater, quickly challenged this. A few months later, he co-authored a paper presenting a mathematical analysis that questioned the very existence of such hydrogen icebergs in the interstellar medium. He demonstrated that the faint starlight permeating the vast vacuum between stars was warm enough to cause any pure hydrogen iceberg, even one formed in the densest and closest molecular clouds, to sublimate and evaporate long before it could traverse the immense distances to reach our solar system. Seligman's initial hydrogen iceberg concept, it seemed, had a critical flaw. Professor Loeb remained convinced that an alien explanation was the most probable. His strong argument sent Seligman back to the drawing board, and the idea of a solid hydrogen iceberg was set aside. However, Seligman's tenacity as a scientist shone through. He continued to explore the core idea that Oumuamua's anomalous motion was due to escaping pure hydrogen gas. His missing piece was a mechanism for how this hydrogen could be trapped and then released. The breakthrough came in 2023 when he collaborated with Jennifer Bergner, an assistant professor at the University of California. Professor Bergner brought a crucial insight from laboratory experiments under extremely cold conditions. Water ice, when irradiated, could effectively trap pockets of hydrogen. Later, when warmed, the ice's structure would rearrange itself, subsequently releasing these trapped hydrogen pockets. This was a revelation. Water ice is abundant in space, and so is cosmic radiation. The cosmic radiation could provide the necessary pre-baking that would allow water ice to encapsulate hydrogen. Together, Seligman and Bergner co-authored a groundbreaking paper arguing that Oumuamua required an entirely new classification. It was neither a regular comet nor a typical asteroid, but something else entirely, a dark comet. This dark comet would possess an invisible coma, present yet undetectable by our observational means. Their refined explanation elegantly accounted for Oumuamua's acceleration and the baffling lack of dust. Dark comets, in this model, wouldn't need to release dusty material. They would simply be reconfiguring their internal structures and gently releasing these pockets of invisible gas rather than violently blasting gas from their surfaces like miniature gassy volcanoes. While this sophisticated theory offered a compelling natural explanation, it was not enough to sway Professor Loeb, who continued to co-author papers accusing Seligman of bad math and persistently advocating for his alien spaceship model. The scientific process, with its robust debates and rigorous challenges, continued to unfold around Oumuamua. Yet, even as the academic discussion continued, Seligman was already looking ahead, extending his logic. If Oumuamua represented a dark comet, could there be other dark comets out there in our own solar system? He, Bergner, and their colleagues embarked on a meticulous search through existing astronomical data. They weren't looking specifically for interstellar objects, but rather for any objects within our solar system that exhibited unexplained acceleration. And astonishingly, they found six distinct objects that displayed non-gravitational, non-solar wind-based acceleration, which could not be attributed to any known mechanism. These objects were small, some as tiny as just 3 meters across. They appeared superficially, like ordinary asteroids, lacking any remarkable features. All of them were near-Earth objects, orbiting close enough to our planet to make potential missions to them highly viable. And, crucially, all were subtly exhibiting signs of acceleration. To be clear, this acceleration was incredibly minor, so slight that it had been overlooked in previous analyses. These objects were not zipping erratically around the solar system like spaceships. Their motions were only slightly off, but consistently so. Much like Oumuamua, conventional science could not account for their subtle deviations, especially given the complete absence of any visible signs of outgassing. Intriguingly, one of these 6 dark comet candidates is already scheduled for a close encounter. In 1999, KY-26 is slated to be visited by the Japanese Hayabusa 2 probe. Originally launched in 2014, Hayabusa 2 successfully completed its primary mission of collecting samples from asteroid Ryugu in 2020. Now, with an extended mission, it's set to visit other asteroids in the near-Earth Apollo group. 1999 KY-26 is a rapidly rotating object, completing a full spin every 10 minutes. Hayabusa 2's mission will involve a flyby to gather more information about this tiny, water-rich object, insights that could prove invaluable for future human missions to Mars. When Hayabusa 2 reaches 1999 KY-26, perhaps the source of its strange acceleration will become clearer. The direct observation of this object might finally shed light on the mechanisms at play. The debate surrounding Oumuamua, whether it was a fragment of a distant broken planet, a piece of alien technology, or a novel natural phenomenon like a dark comet, might find its long-awaited resolution. With Oumuamua now far beyond the reach of our most powerful telescopes, direct study is impossible. We may never know its true nature with absolute certainty. But the discovery of these new, similarly perplexing objects, particularly one we can visit, offers a tantalizing path forward. If Hayabusa 2 confirms invisible outgassing of hydrogen, Seligman's dark comet theory will gain immense validation. However, if some unforeseen, truly anomalous characteristic is revealed, perhaps even a tiny hatch opening to reveal an alien form, well, then Professor Loeb's bold proposition might demand more serious consideration. It's a fascinating prospect, though the former seems far more likely than the latter, especially since 1999, KY-26 has been imaged well enough for us to be fairly certain it is not a light sail. Ultimately, it's quite possible that neither current theory is entirely correct. That is the enduring wonder of science. The more we delve into the universe, the more we encounter strange and unexpected phenomena. Each new observation, each new anomaly, refines our understanding and pushes the boundaries of our theories. Perhaps one day, we will encounter more objects like Oumuamua from beyond our solar system, and their collective behavior will lend decisive weight to a particular explanation. The very act of searching, even for dark objects that currently seem to act under invisible forces, fills us with a marvelous sense of curiosity. When 2031 rolls around, perhaps that itch for answers will finally be scratched, or perhaps, as is often the case in science, we will simply be faced with even more profound questions. Only time, that silent companion of the cosmos, will tell. Take another gentle breath. Allow the grandness of these ideas to settle over you. The universe is a vast, intricate tapestry woven with threads of known physics and shimmering strands of mystery. Oumuamua, a fleeting whisper from beyond, reminds us that our cosmic neighborhood is full of surprises, and that even the most subtle deviations can hint at profound new understandings. There's a quiet beauty in not knowing everything, in the gentle pursuit of understanding the unknown. It is a journey of constant discovery, where every new question illuminates a path to further contemplation. Now, let the stillness embrace you as we drift deeper into the wonders that remain just beyond our grasp. The quiet hum of the cosmos invites you to simply be, to let your thoughts float like distant stars. Now, let us gently shift our gaze from the distant whisper of Oumuamua to something perhaps closer to home, yet equally, if not more, enigmatic. We will explore a topic that has danced on the edge of human understanding for decades, often dismissed with a skeptical sigh, yet now, surprisingly, commands serious attention from the most unexpected corners: unidentified aerial phenomena, or UAPs. You might know them by their older, more familiar name, UFOs. But the shift in terminology itself hints at a deeper change, a new willingness to look at the skies with fresh eyes, to acknowledge that something unusual is indeed going on. For a long time, the mere mention of flying saucers would conjure images of grainy, shaky videos, of fantastic tales told by enthusiastic but often unreliable witnesses. There was a pervasive stigma, a quiet eye roll associated with anyone who claimed to have seen something truly inexplicable in our skies. Yet, as with many aspects of science, what was once dismissed as folklore can, with enough persistent evidence, begin to shed its mythical shroud and step into the light of rigorous inquiry. The modern era of UFO sightings often traces its roots back to a pivotal moment in 1947. Imagine the scene: an American businessman named Kenneth Arnold was flying his private plane near Mount Rainier, a majestic peak reaching for the heavens. As he soared through the vast, clear sky, he claimed to witness something extraordinary. Not one, but 9 crescent-shaped silvery objects moving at astonishing speeds, thousands of kilometers per hour, defying any known aircraft technology of the time. He described their motion as being like saucers skipping on water, a phrase that, perhaps more than the sighting itself, embedded the term flying saucer into the collective consciousness. Initially, he, like many others, wondered if they might be secret military jets, a plausible thought in the immediate aftermath of a global conflict. But soon, he and other witnesses began to ponder a more audacious possibility. Could these objects be extraterrestrial? The media, always keen for a compelling story, eagerly embraced Arnold's vivid description, and the idea of flying saucers took flight across the nation. Before long, others began to report their own alleged encounters, feeding a burgeoning fascination with the unknown. The United States, fresh from the technological marvels of wartime innovation, became captivated by the possibility of visitors from beyond. However, the U.S. military, while initially alarmed by reports of unknown aircraft in their airspace, a perfectly rational concern for national security, especially right after World War II, did not share the public's immediate leap to extraterrestrial conclusions. They established various programs to investigate these sightings, seeking to determine if they posed a threat or if they were simply misidentifications. The most well-known of these was Project Blue Book, which operated until 1969. Over its lifespan, Project Blue Book meticulously collected a staggering 12,618 UFO reports. Yet, its ultimate conclusion was that almost all of these reports were the result of misidentifications of conventional aircraft, natural phenomena, or, in a smaller percentage of cases, lacked sufficient data to draw a definitive conclusion. With such a seemingly damning report, the U.S. government officially ceased funding for such investigations, and the formal inquiry into UFO sightings came to a halt. Partly as a direct consequence of Project Blue Book's findings, a palpable degree of stigma became associated with seeing a UFO. Anyone who dared to claim such an experience was often met with ridicule, labeled as delusional, or simply dismissed as someone with an overactive imagination. The prevailing sentiment boiled down to a fundamental question of evidence: if aliens were truly real, and if they were truly visiting our planet, then where was the undeniable, incontrovertible proof? Of course, to answer that, we first need to define what we would consider to be reliable proof. Imagine, for a moment, that a person approaches you, their eyes wide with conviction, claiming they just witnessed a silver disc shoot across the sky at a speed far exceeding anything a human-made airplane could achieve. Would a single person's account be enough for you to conclude, definitively, that they had seen an alien spacecraft? Probably not. Human memory, as we know, is remarkably fallible. Even if you trust the character of the person, believing they are not intentionally fabricating a story, they might be misremembering crucial details. Or perhaps they misjudged the true speed or distance of what they saw due to an optical illusion or a trick of perspective. Our perceptions, while often incredibly accurate, can also be easily swayed by context, emotion, or even the subtle nuances of light and shadow. "Ah," they might cry, "but I recorded it on film." You eagerly examine the evidence, but unfortunately, the video they provide is grainy, shaky, and offers only a blurry, fleeting glimpse of the alleged spacecraft. Is that proof again? You might well remain skeptical, even if the video is not a deliberate hoax. And let's be honest, in this digital age, it is remarkably easy to fabricate compelling visual evidence. It could be a digital artifact, a glitched pixel on the camera sensor, or simply some natural or man-made phenomenon that neither of you had ever encountered before. The vast array of optical effects, atmospheric conditions, and human-made objects in our skies means that what appears inexplicable to the untrained eye may have a perfectly mundane explanation. So, what, then, would constitute truly good proof of an alien spacecraft? Ideally, for any scientific mind, the evidence would need to be seen by multiple trustworthy people, ideally trained observers whose accounts could be cross-referenced and corroborated. The more, the merrier, for collective observation often filters out individual biases and errors. Furthermore, such an event would ideally be recorded by multiple pieces of hardware, cameras, radar systems, infrared sensors, to eliminate the risk of it being a mere technological glitch or a single faulty instrument. The recorded data would have to display characteristics that completely ruled out its being any known man-made phenomenon or any natural event. Best of all, it would be repeatable. If the phenomenon kept occurring, it would provide more opportunities for study, allowing scientists to systematically rule out other causes, to gather more data, and to build an increasingly robust case for its truly anomalous nature. And this precisely brings us to the pivotal event that began to shift the paradigm, to pry open the closed files, and to force a reevaluation of what was previously unthinkable. It brings us to the year 2004 and the USS Nimitz. Imagine the vast expanse of the Pacific Ocean near Southern California in November 2004. The Navy aircraft carrier USS Nimitz was engaged in a routine training exercise, its immense presence a testament to human engineering. Nearby, another vessel, the USS Princeton, had recently undergone significant upgrades to its radar system, enhancing its capabilities to detect and track objects in its operational area. Soon after these upgrades, the Princeton began noticing strange aircraft in the area. These craft were behaving in ways no known aerial vehicle could. They were observed descending from an astounding altitude of 80,000 feet down to 20,000 feet in blistering speeds, a vertical drop that defied the laws of aerodynamics for conventional craft, before either vanishing completely from radar or, just as inexplicably, shooting back up into the sky. This went on for several days, a persistent, unsettling presence that couldn't be ignored. Finally, the Princeton called in the Nimitz, requesting that fighter jets be scrambled to investigate. 2 FA-18F Super Hornet jets were launched. Each jet carried a weapons camera, a crucial detail, but no actual weapons, as this was, after all, a training exercise. Each jet had 2 highly trained pilots on board. Upon arriving at the designated location, all 4 pilots quickly spotted what they were looking for. Below them, a strange, featureless, tic-tac-shaped object was moving in a bizarre, erratic manner, zipping back and forth above a patch of frothy, boiling water in the sea. It had no visible means of propulsion, no wings, no rotors, no exhaust plumes. It was described as being roughly the size of a jet fighter, with a whitish, smooth, almost featureless surface. Suddenly, the object stopped its erratic zigzagging. It seemed to have detected their presence. In an instant, it whipped around and began traveling up towards the jets, as if intending to meet them head-on in the air. But then, just as quickly, it accelerated away with a speed that surpassed anything the seasoned pilots had ever witnessed. Baffled and awestruck by what they had just experienced, the pilots returned to base. Only then were they informed by the radio operator that the craft they had just encountered had been tracked again, but it was now over 60 kilometers away, having covered that immense distance in under a minute from the moment it left the pilot's visual range. This was no ordinary sighting. This was an object observed not by a single, potentially unreliable witness, but by 4 trained professional military pilots on duty. It was simultaneously recorded by aircraft cameras and tracked by modern advanced ship-based radar from one of the most technologically sophisticated navies in the world. This incident, with its multiple corroborating sources of evidence, ticked many of the crucial boxes for what constitutes truly reliable proof. The report was logged, but initially, no grand announcements were made. You might simply dismiss this as a strange, isolated anecdote, were it not for the fact that this authenticated footage of the event was later confirmed by the U.S. government itself in a Freedom of Information Act request. But the truly extraordinary aspect of this incident was that it kept happening. The phenomenon, far from being a singular event, began to repeat. Navy and Air Force pilots, those who routinely operate in our national airspace, were spotting strange, inexplicable objects in the sky with alarming frequency. Some were even claiming it was an almost daily occurrence. Many pilots, initially, were hesitant to mention what they had seen, fearing the ridicule and professional stigma that had long been associated with UFO sightings. Yet, as the encounters became more common, the sheer volume of reports became impossible to ignore. The Navy, recognizing a growing operational safety concern, began issuing standardized reporting cards to be kept in pilots' kneeboards in their cockpits, outlining what to do in the event of such a sighting. Between 2004 and 2021, a total of 144 reports came in from Navy personnel describing encounters with unidentified objects in the sky. Of these, a remarkable 80 were observed by multiple sensors, further reinforcing their veracity. There were 11 recorded accounts of near misses with jets, and perhaps most telling of all, only one of these 144 incidents could be positively identified and explained. Then, between 2021 and 2022, sensing that there might indeed be something profoundly significant to all this, the Navy took a crucial step. They began actively destigmatizing the reporting process, openly encouraging their pilots to record and report anything unusual they encountered. The response was immediate and overwhelming. A staggering 247 new reports poured in, and an additional 119 incidents were reported to have occurred in the past, now that pilots felt safe to disclose them. This meant that, for a period, there was almost one new unidentified aerial encounter every other day. In total, the cumulative number of unidentified objects reported to the authorities had surged to 510. So, what were these objects? Their natures, and presumably their origins, seemed to vary. Some behaved like drones, with the Navy even detecting radio signals emanating to and from them. Yet, these particular drones stayed airborne for far longer than any commercially available drone on the market was capable of doing, suggesting a technology beyond public access. Others were more akin to conventional aircraft, moving in formations, yet exhibiting previously unheard of levels of acceleration and maneuverability. Some displayed truly astonishing capabilities, able to both fly through the air and submerge underwater, seemingly at will, transitioning between mediums seamlessly. Still others acted like balloons, yet possessed unknown means of remaining aloft, sometimes defying strong wind currents by remaining completely motionless, or even moving directly against them. No doubt, among those 510 reports, some will eventually prove to be simply glitches in technology. For instance, a famous video showing a strange triangle in the sky is now thought to not truly be that shape. Instead, the unique design of the night vision goggles used to record it is believed to be distorting the light, an effect similar to lens flare but specifically tailored to that particular technology. However, even in such cases, it remains concerning that the Navy did not know what these drones were, or why they were circling a U.S. Navy vessel during night training exercises. Recognizing the need for a neutral, less sensational term, the Navy began referring to these objects as UAPs, or unidentified aerial phenomena, in the hopes of removing the negative connotations historically associated with UFOs. More recently, this term has evolved again to unidentified anomalous phenomena UAP, broadening the scope to include objects that might not be strictly aerial. And while the government agencies involved do not wish to assume an alien origin, they are also no longer ruling it out. They publicly reported their findings in a congressional hearing on May 17, 2021, and are now regularly and somewhat transparently publishing reports for the general public about the ongoing investigation, provided it doesn't compromise classified sources or technologies. Their current focus is on collecting as much high-quality data as possible, understanding that this is the only path to better science and, ultimately, to understanding. This methodical, data-driven approach marks the biggest shift of all. When you see a government, especially one as historically cautious as the U.S., reaching out to the wider scientific community and openly asking, what are these things we keep seeing? It strongly confirms that there is indeed something significant to see. All in all, it certainly makes you wonder. Of course, it's possible that all of this might ultimately prove to be technology belonging to rival nations. Governments around the world are perpetually engaged in developing new, secret technologies, and they are hardly likely to admit to them publicly. However, it is telling that America itself does not seem to believe these phenomena are their own. According to the UAP Task Force's official reports, they also have no knowledge of these technologies belonging to other countries. This leaves a vast void of explanation. Perhaps I will leave you with this powerful final quote from NASA Chief Bill Nelson. NASA is one of the agencies working with the UAP Task Force to figure out the nature and origins of these phenomena. They are lending their task force experts to help rule out any natural phenomena that NASA is aware of, and they don't know what it is, and we don't know what it is. We hope it's not an adversary here on Earth that has that kind of technology, but it's something, and so this is a mission that we're constantly looking at. Who is out there? Who are we? How did we get here? How did we become as we are? How did we develop? How did we civilize? And are those same conditions out there in a universe that has billions of other suns and billions of other galaxies? It's so large, I can't conceive it. What do you think? Could these phenomena have innocent human explanations that are simply beyond public knowledge? Or are you convinced there's something more to them, something that can only be explained by life beyond our planet? The beauty of the unknown is that it invites all possibilities into the quiet space of contemplation. Let these thoughts drift gently through your mind. The idea of the unknown, of unexplained aerial phenomena, can be unsettling, but here, in this calm space, it transforms into an invitation for wonder. Imagine the vast, boundless sky above you, stretching infinitely into the cosmos. How many secrets does it hold? How many movements? How many lights? How many whispers go unnoticed, or are simply misinterpreted by our limited senses and technologies? The history of science is replete with instances where what was once considered impossible or even ridiculed eventually became understood reality. The very concept of gravity, once a mysterious force, is now a fundamental pillar of our understanding of the universe. The existence of black holes, once theoretical curiosities, are now directly observed. Perhaps UAPs are simply a new frontier of atmospheric physics, or perhaps they hint at a technological leap we cannot yet conceive, or perhaps they are indeed a subtle call from beyond. There is a serene acceptance in embracing this uncertainty, in allowing the mind to wander without demanding immediate answers. It is a state of quiet curiosity, a gentle embrace of the vastness of what we do not yet comprehend. Let your thoughts float like clouds in the twilight sky, moving slowly, peacefully, carried by the gentle currents of wonder. The very existence of these UAPs, now acknowledged and investigated by serious minds, underscores a profound truth. The universe, even our immediate cosmic backyard, is far stranger and more mysterious than we often dare to imagine. And within that mystery lies a profound sense of peace, a reminder of how small, yet how wonderfully curious we truly are. This journey of exploration is endless, and each new riddle is merely a new invitation to look deeper, to listen more intently to the whispers of the cosmos. Let us now turn our thoughts to an even grander mystery, one that stretches across the unimaginable vastness of our universe, reaching out to billions of galaxies, each containing billions of stars. It is the profound, almost aching question that has quietly pondered in the minds of thinkers for generations. Are we alone? The search for alien life, for even the faintest whisper of another civilization, has inspired countless endeavors. Scientists have dispatched data-collecting rovers to the rust-colored plains of Mars, seeking traces of ancient microbial life. Astronomers have patiently listened across the vast cosmic radio dials with colossal telescopes, hoping to intercept a signal, a coded message, a fleeting pulse that says, Hello, you are not by yourselves. And satellites, laden with information about our own small blue planet, have been launched outwards, carrying silent messages of our existence into the cold, dark embrace of interstellar space. All this relentless searching, this quiet yearning, stems from a simple, yet deeply felt, conviction for many of us in the infinite expanse of a universe so immense, a universe that has existed for some 13.8 billion years. It seems almost incomprehensible that life, especially intelligent life, would arise only once on this single, fragile world. If even a tiny fraction, say just 1%, of the countless planets in our own Milky Way galaxy were to harbor life that then evolved into civilizations capable of reaching out into the cosmos, we should, theoretically, be witnessing signs of thousands, if not millions, of alien races. Their signals, their light, their very presence should be abundant, a cosmic symphony filling the night sky. Yet, as we gaze into the silent darkness, a profound question echoes in the void, a question famously articulated by the Nobel Prize-winning physicist Enrico Fermi in his renowned Fermi paradox: where is everyone? Why? If the universe is so vast and the conditions for life potentially so widespread, do we not see, hear, or detect any obvious signs of these countless advanced civilizations today? We will gently explore some of the possible answers to this enduring paradox, because while we cannot say for certain whether aliens exist, there are surprisingly intricate barriers and subtle limitations that might prevent us from seeing them, even if they do. Let us first address the most straightforward, though perhaps least comforting, possibility. Maybe there's simply no one to see. In the grand cosmic lottery, it might be that the odds of life arising from non-living matter are extraordinarily low, or that the leap from simple life to intelligent, technologically advanced civilization is a hurdle so immense that only a minuscule fraction of life-bearing planets ever make it this far. If this is true, then it's entirely plausible that the skies remain empty of ships and signals simply because we are, truly, the first ones to ever reach this point of cosmic awareness. All other planets, for now, could be empty and desolate, silent cosmic rocks adrift in the dark. If that were the case, then the immense opportunity would fall to us to spread out across the universe, to discover these empty worlds. And the only life we would ever encounter would be that which we ourselves carry from Earth. While this remains a perfectly reasonable possibility, one for which there is no conclusive evidence to disprove, it is certainly not the only explanation for the silent skies. We must also acknowledge that our ability to discover or make contact with an alien civilization is constrained by surprising natural limitations. For us to truly connect, one of two things generally needs to happen. Either we must send a message out into the cosmos and then patiently await a response, or an alien civilization must make the first overture, sending a message directly to us. There are various ways one might attempt this, perhaps by sending manned spaceships across the interstellar void, or by dispatching unmanned probes to scout distant star systems. However, there are significant, almost insurmountable issues with attempting anything beyond the mere sending of messages. Consider the immense challenge of sending a spaceship. At the current speeds our most advanced spacecraft are capable of, interstellar travel is a staggering endeavor. To reach even the nearest star, Proxima Centauri, which is a mere 4 light-years away, would take over 81,000 years. Imagine that 81,000 years, or roughly 2,700 human generations. This is assuming, of course, that we happen to have alien neighbors literally next door. To traverse the vast distances of the galaxy, which is roughly 100,000 light-years across, would take millions of years, a time scale that utterly dwarfs any human civilization we have ever known. Even if we allow for future technological improvements, the energy required to accelerate an object anywhere near the speed of light is colossal. For reasons we won't delve into too deeply here, mass simply does not like to travel at those speeds. As an object approaches the cosmic speed limit, its effective mass increases dramatically, requiring an ever-increasing amount of energy to accelerate it further. Indeed, to accelerate a human-sized spacecraft to true light speeds would require more energy than exists in the observable universe. So, unless we, or our potential alien friends, are able to discover some kind of revolutionary workaround, perhaps harnessing exotic physics like warp bubbles that move space around a craft rather than moving the craft itself, the most likely, and certainly the easiest, way to communicate with other civilizations is through the gentle medium of radio signals. It's worth a moment to consider these warp bubbles, a fascinating theoretical concept. Scientists have hypothesized some promising ideas that involve subtly manipulating the fabric of space-time itself, effectively moving the local area of space around a craft, rather than accelerating the craft within that space. The speed of light limit, as we understand it, only applies to movement within a local area. If it's your local area that's doing the moving, then theoretically, you're fine. We actually have examples of such phenomena in nature around black holes, where space-time itself is warped and dragged. But until such a scientific reality becomes tangible, let us simply accept the current cosmic truth. It's far easier to make a call than to pay a visit. Sending light or radio waves is significantly simpler and cheaper, akin to merely flipping on a sufficiently powerful light bulb. So, let's assume that our first contact with an alien civilization will occur through the exchange of radio signals. Even here, however, we encounter a fundamental roadblock. Radio signals and light waves are perfectly capable of traveling at relativistic speeds. It's called the speed of light for a reason. After all, approximately 300 million meters per second. But that speed, while seemingly instantaneous from our perspective, is still a finite limit. No signal, no information can travel faster. This cosmic speed limit, in turn, dictates how far we can effectively see and communicate across space. Imagine we send a signal out into the cosmos. It must travel for years, decades, centuries, or even millennia before it reaches an alien civilization. And then, even if they decide to respond immediately, their reply must travel all the way back to us. We only invented and widely utilized radio technology in the mid-1890s. This means that, realistically, we have only been actively capable of broadcasting our presence and actively listening for a little over a century. As such, we would only be able to exchange a two-way message with aliens who live at most around 60 light years away from us. A signal sent out in 1900 would take 60 years to reach an alien civilization at that distance, and another 60 years for their reply to return, meaning the earliest we could hope for a response would be 2020. Our entire galaxy, remember, is roughly 100,000 light years across. The 60-year light bubble within which we could have had a full conversation is truly tiny, a mere pinprick in the vastness of the Milky Way. To be fair, this particular limitation diminishes if the aliens contact us first. After all, the light we are currently receiving with the James Webb Space Telescope has been traveling for over 13 billion years, originating from nearly the very beginning of the universe. If an alien civilization came into being, say, 2 billion years ago and has maintained its existence since then, that means they now effectively have a 2 billion light-year bubble from which we could theoretically observe their light or signals. A civilization 10 billion years old could have a 10 billion light-year bubble. But if they were 10 billion light-years away and only 9 billion years old, they would remain completely invisible to us, their signals still traveling across the immense void. So, assuming such far-off aliens exist and are technologically advanced, why aren't we seeing any of their signals? Perhaps this line of thought rests on a faulty assumption that there haven't been any signals coming in from the stars. The truth is, there have been signals. We're just not entirely sure what they are. Let us explore this with a particularly fascinating example that has captivated scientists and enthusiasts alike for decades. In 1961, driven by the profound pursuit of evidence for extraterrestrial intelligence, researchers at The Ohio State University completed work on a specialized radio telescope named Big Ear. This colossal instrument, spanning the size of 3 football pitches, was designed to capture faint radio signals from the cosmos. It operated much like modern telescopes, funneling incoming waves from a large reflector to smaller mirrors, and finally into 2 central receivers, where the data was processed. Its unique design, featuring wireframe capture dishes rather than solid mirrors, reflected its purpose as a radio telescope, not an optical one. Big Ear's design, while innovative and cost-effective, imposed a certain limitation. It couldn't freely rotate and point in any direction like a conventional dish. Its primary reflector could only tilt up and down, meaning it was somewhat confined to listening to a narrow strip of space at any given moment. However, its ingenious designers found a clever workaround. They built Big Ear at precisely the right orientation so that the Earth's own rotation would provide its left-to-right sweep across the sky, with the planet turning it one way and its tiltable reflector adjusting along the other axis. One could, with enough patience, point Big Ear towards virtually any point in the heavens. It was a remarkably clever solution. Big Ear's direction of attention would slowly sweep across the night sky in wide, circular arcs, patiently listening for any unusual signals that defied a natural explanation. And then, in 1977, Big Ear found something truly extraordinary. On the evening of August 15th, a 72-second-long pulse of radio waves arrived, a signal so powerful, 30 times stronger than anything Big Ear had ever heard before in the background chatter of the universe, that the researcher who discovered it, Jerry Eman, scribbled "wow" on the computer printout. This spontaneous exclamation gave the signal its enduring historical name, the wow signal. The signal itself was remarkably uniform. It rose steadily in intensity, peaked, and then smoothly dropped back down. A clean, consistent profile, unlike the erratic fluctuations typically expected from cosmic radiation. This uniformity suggested that whatever had produced the signal was broadcasting with deliberate consistency, much like the focused beam of a lighthouse sweeping across the stars, briefly illuminating us as it passed, and then moving on. Except it didn't return. Due to Big Ear's design, researchers had to wait a few minutes before the Earth's rotation would bring the telescope's focus back to that particular patch of space from which the wow signal had originated. But when they returned, the signal had vanished. Despite numerous attempts to check back in from time to time, over the decades that followed, we have never heard another wow signal from that precise region of space. So, what was it? Was it a fleeting fault in Big Ear's intricate machinery, a momentary malfunction in its vast electronic brain? Was it a passing comet, or some other unknown natural phenomenon that coincidentally threw out a momentary burst of signals, an astrophysical event we simply don't yet understand? Or was it truly an alien civilization sending a brief, powerful message across the light years, a cosmic greeting that we, perhaps, only caught a single tantalizing note of? The fact of the matter is, we don't know. It's entirely possible that the wow signal has a perfectly natural, though as yet undiscovered, explanation. After all, when the regular, consistent pulses of X-rays from pulsars were first detected, some people initially speculated that they might be aliens trying to communicate, before the true astrophysical explanation was found. Perhaps one day we will find another wow signal or a new understanding of cosmic phenomena, and we will realize that its origin was not alien at all. But there's a crucial technical point to consider here, one that often gets overlooked. If you were a scientist in charge and you detected such a powerful, unique signal, you would instinctively point your telescope at that exact spot in the sky and simply wait. You would wait for hours, days, weeks, months, or even years, hoping to detect another signal, to confirm its presence, to study its characteristics in detail. If you didn't, another signal might come in, and you'd miss it. Now, recall the way Big Ear was constructed. It rotates only within the confines of the Earth's rotation. It physically cannot stay focused on the same place in the sky for more than a few moments at a time. As such, we have no idea whether more signals came in from that specific region of space or not. Hundreds could have arrived over the next several hours, an entire symphonic performance of alien communication. But because Big Ear was not listening in that direction for more than a fleeting moment in the day, it would have only ever caught a single isolated note. This fundamental limitation highlights a conscious decision on the part of organizations like SETI, the search for extraterrestrial intelligence, because resources are limited and space is unimaginably vast. SETI and similar initiatives lack the time, funding, and dedicated telescope capacity to take one powerful instrument and point it for potentially decades on end at a single promising spot, just to see if aliens decide to speak to us again from that particular cosmic address. Instead, they largely favor broad sweeps of the sky, covering as much ground as possible, hoping to get a lucky hit, a powerful, undeniable signal that screams artificial even in a brief encounter. This approach is more reasonable than my analogy of a fisherman casting and casting, rather than leaving a line in the water, might make it sound. Alien civilizations, if they exist, are not fish to be attracted by a lure or scared off by the splash of a telescope looking at them. And while the focused, long-term observation process is certainly more methodical, there's always a chance that a sweeping survey will indeed encounter some compelling evidence or signal. The primary problem, however, comes with the crucial follow-up. The truth is, there have actually been numerous signals, much like the WOW signal, that radio telescopes have picked up over the years. Strange, unusual bursts and patterns that we currently have no natural explanation for. But because we aren't focusing on them, because we aren't thoroughly following up with years of continued, dedicated study, we are missing a lot of crucial information. And as a result, we often end up with weaker, less conclusive findings. This brings us back to our paradox. Perhaps we are seeing no aliens simply because of the limitations of our chosen method, a method necessitated by the sheer scale of the search. Of course, these are just a few of the many possible theories that attempt to answer the Fermi paradox. For this quiet contemplation, I've tried to focus on some of the technical and observational limitations to finding signs of alien life. However, there are other, more theory-based explanations that lean more heavily on speculation. Ideas like the Great Filter, the Dark Forest hypothesis, or even the zoo hypothesis. Fascinating concepts that offer intriguing insights into our own civilization and place in the cosmos. Perhaps if you find this subject as captivating as the silence of space, we can explore those ideas in a future reflection. Do you believe there are aliens out there in the vast night sky? If so, why do you think they've remained silent? Or why have we seemingly failed to truly hear them? The wonder lies in the asking, not just in the knowing. Let your thoughts unfurl, like the gentle spiral arms of a galaxy. The search for alien life is not merely a scientific endeavor. It is a profound philosophical quest. It asks us to consider our own place, our own uniqueness, and the incredible fragility of life itself. The silent cosmos, far from being empty, is filled with potential, with possibilities that stretch the very fabric of our imagination. Feel the quiet rhythm of your breath. The universe doesn't shout its secrets, it whispers, and sometimes its whispers are so faint, so subtle, that we need to learn to listen in entirely new ways. Perhaps the silence is not a lack of sound, but rather a frequency we haven't quite tuned into yet. This quiet waiting, this patient listening, is a profound act of hope. It reminds us that the universe is vast enough to hold all possibilities, and that our journey of discovery is truly infinite. Let that thought bring a deep sense of calm, a gentle drifting towards the quietude of understanding, or perhaps, simply, of peaceful rest. Let us now gently draw our focus back to our own planet, to the very air that surrounds us. A familiar blanket of atmosphere that often holds secrets far more astonishing than we might imagine. While we gaze upwards at the cosmic dance of stars and speculate about distant visitors, there are phenomena right here on Earth, swirling within our own skies, that continue to defy complete explanation. In recent years, researchers have meticulously documented a captivating array of these previously unproven, or even entirely unknown, atmospheric events. Think of the breathtaking, transient, luminous events, the towering red sprites that flash briefly above thunderstorms, the vibrant blue jets that shoot upwards into the stratosphere, the vast, shimmering, gigantic jets that connect thunderclouds to the edge of space, and the ephemeral elves, expanding rings of light in the ionosphere. We've also begun to understand the mysterious beauty of noctilucent clouds, those ethereal silver-blue wisps, visible only at twilight against the deepening night sky, and observed rarely seen variants of familiar phenomena, such as a fleeting glimpse of green lightning or the haunting glow of red auroras painting the polar heavens. These are just a few glimpses into the incredible occurrences we've been able to observe, verify, and begin to understand, thanks to the amazing advances in our technology and research capabilities. Yet, despite these leaps in our understanding, there remain certain phenomena that are almost completely outside our current ability to definitively prove. Of these, none is perhaps stranger, or more terrifying in its historical accounts, than ball lightning. It is an alleged electrical occurrence so mind-boggling, so utterly fantastical in its reported behavior, that it sounds, well, entirely made up. Imagine, if you will, a glowing sphere of light floating serenely through the air, sometimes as small as a golf ball, sometimes as large as a beach ball, or even bigger. It might drift quietly into a room through a closed window pane, hover for a moment, and then vanish with a silent pop or a violent explosion. This is the essence of ball lightning as reported by countless witnesses across centuries. It's a phenomenon that has been reported so many times and has received such persistent scientific scrutiny that it occupies an unusual, almost liminal place between established science and ancient folklore. But unlike most myths, ball lightning carries with it a mounting body of tantalizing evidence suggesting that we should not only take its existence seriously, but that we might, perhaps surprisingly, already have subtle proof that it does indeed exist. So, what exactly is ball lightning? How are dedicated scientists, with their modern laboratories and advanced tools, attempting to reproduce it? And if it is, as many experts believe, a real phenomenon, why is it so incredibly difficult to prove, to capture, to pin down with the cold, hard certainty of scientific observation? Let us embark on a gentle journey through the fascinating history of ball lightning encounters, examine some of the most intriguing new theories that have emerged, and learn about the stunning laboratory experiments that are attempting to get to the bottom of one of science's strangest, most enduring unsolved mysteries. As always, this is a space for quiet contemplation, not for definitive answers or medical advice. For centuries, accounts of ball lightning have emerged from every corner of the globe, whispered from ancient texts, recorded in ships' logs, and recounted in hushed tones by eyewitnesses. While the stories vary in their dramatic flair, many consistently agree on certain core details. The phenomenon invariably appears as a bright, burning orb, its color often described as white or blue, though sometimes appearing red, orange, or yellow, like a miniature, self-contained sun. It is said to last anywhere from a fleeting second to several seconds, or even minutes in rare instances. The orb often floats along a slow, deliberate path, sometimes changing direction with an unnerving, almost intelligent erraticism. Perhaps most astonishingly, it has been alleged to pass through solid walls and closed windows unscathed, as if matter itself posed no barrier to its ethereal presence. According to some reports, the ball lightning simply dissipates with a soft fizzle, fading away like a dying ember. In others, it explodes violently, unleashing destructive force that can cause severe damage, leaving behind a distinctive odor, often described as sulfurous, like the lingering scent of ozone after a powerful electrical discharge. At its most destructive, ball lightning has been reported to maim and even kill people, and to blast apart heavy walls, sturdy doors, and even the stout timbers of ships. Now, in this tranquil space of scientific exploration, we understand that anecdotal evidence, no matter how compelling or numerous, cannot be considered definitive proof. True scientific confirmation requires observation under controlled conditions, meticulous testing, and, ideally, the ability to repeatedly reproduce the phenomenon in a controlled environment. So, with that understanding in mind, let's turn our attention to a few of the alleged ball lightning encounters that I find most intriguing, precisely because they are so detailed and so puzzling. Imagine the high seas in 1739. The sailing ship Catherine and Mary was navigating the treacherous waters off the Gulf Coast of Florida when it was engulfed by a sudden, deadly thunderstorm. According to a harrowing eyewitness account, a large ball of fire descended from the heavens, striking the ship with immense force. The report claims it split our mast in 10,000 pieces, killed one man. Another had his hand carried off. The account chillingly adds, "Had it not been for the violent rains, our sails would have been a blast of fire." It's a dramatic, almost unbelievable story, yet it speaks to the destructive power attributed to these mysterious orbs. The narrative grows even stranger in 1753 with a tragic account involving Georg Richmann, a renowned professor and pioneering electrical researcher in St. Petersburg. Richmann was attending a conference when he noticed a storm approaching, a perfect opportunity for his experiments. Eagerly bringing an engraver to record his observations, a testament to the scientific rigor of the time, he hurried to conduct a kite experiment, similar to the groundbreaking work Benjamin Franklin had performed the previous year. As reported by the horrified engraver afterwards, Richmann was in the midst of his experiment when a fiery blue orb, described as an electric globule, was seen to crawl down the string of the kite. It fatally struck him, a direct, deadly blow, instantly knocking the engraver unconscious. The subsequent autopsy reportedly found a coin-sized red mark on the professor's forehead and injuries consistent with severe electrocution. This account, with its scientific context and the specific tragic outcome, lends a chilling credibility to the destructive potential of ball lightning. Perhaps one of the most compelling modern eyewitness accounts, particularly because it comes from a trained observer, is from 1963. R.C. Jennison, a respected researcher at the University of Kent, was flying late at night from New York to Washington. Jennison, seated in the cabin shortly after midnight, watched as the plane became completely enveloped in a brilliant electrical discharge. Within seconds, a bright, glowing sphere, estimated to be about 20 centimeters in diameter, appeared. Most remarkably, it emerged from the pilot's cabin and traveled the entire length of the aircraft, silently passing through the aisle before disappearing. In 1969, Jennison, a scientist known for his meticulous observation, published a detailed account of his experience in the prestigious journal Nature, adding significant weight to the phenomenon's reality. Due to these credible reports, and many others like Jennison's, scientists have, despite the skepticism, taken the phenomenon of ball lightning seriously. They have put forward numerous theoretical models in an attempt to explain its bizarre behavior within the known laws of physics. One theory proposes that ball lightning could, in some cases, be a hallucination, a trick of the mind triggered by the intense magnetic fields present close to a lightning strike. This idea draws parallels with similar visual hallucinations experienced during epileptic seizures, which can sometimes be induced by strong electromagnetic fields. This theory suggests that ball lightning might, at times, be a figment of a stimulated occipital lobe, the visual processing center of the brain. However, if this theory were universally true, it would seemingly contradict the numerous reported instances of physical damage caused by ball lightning, such as the tragic death of Georg Richman or the destruction observed on the Catherine and Mary. Another long-standing hypothesis proposes that ball lightning is a form of contained plasma reaction. You might be familiar with St. Elmo's fire, the mesmerizing phenomenon famously observed on the masts of ships during storms, where the voltage difference between the air and the ground becomes great enough to ionize the air molecules, causing them to glow with highly excited particles. According to this theory, ball lightning would be a more complex, self-contained bubble of plasma. This plasma might behave as a solid and a self-reinforced wave that can maintain its shape and move at a constant velocity without dispersing, a stable pocket of ionized gas. Don't worry if this concept feels a little confusing. We are touching on a particularly complicated subject that even researchers are still striving to fully comprehend. The precise mechanism for how such a plasma ball could be stable, self-contained, and move freely remains a significant challenge for this theory. Perhaps one of the most promising and widely discussed hypotheses was put forth by John Abrahamson and James Dennis at the University of Canterbury, Christchurch, in the year 2000. Their model proposes that a powerful positive lightning strike, when it hits soil, can vaporize tiny particles of silicon dioxide, along with carbon and other common soil elements. These vaporized molecules, energized by the immense heat and electricity of the strike, then react with oxygen in the air. This chemical reaction, involving energized nanoparticles of silicon, carbon, and silicon carbide, would produce light and heat, forming a glowing, self-sustaining ball. The key here is that these silicon nanoparticles would be extremely reactive and could continue to oxidize, essentially burning slowly and steadily, explaining the orb's persistence and luminosity. Remarkably, this specific model received a tantalizing piece of indirect support from a strange incident that occurred a decade ago in Lanzhou, China. You might recall me mentioning that there weren't any truly verified instrumented recordings of ball lightning. Well, that may not be entirely true, or at least this incident comes exceptionally close. In July 2012, researchers from Northwest Normal University had set up spectrometers to meticulously record ordinary lightning strikes. During a powerful lightning event, their instruments, quite by chance, recorded something extraordinary, a glowing wide orb. The orb had an estimated glow of 5 meters across, initially white, which then turned red as it traveled for 10 meters before silently ascending into the air. Crucially, All of this was captured with high-speed video, though sadly, this video has not been widely made public, and the spectrometer readings were preserved. The spectrometer, a device that analyzes the light emitted by a substance to determine its composition, confirmed the distinct emission lines from silicon, calcium, and iron, all elements commonly found in soil. If this observed phenomenon was, in fact, ball lightning, as it strongly appears to be, then this invaluable data adds potent evidence to support the vaporized silicon hypothesis, suggesting that at least some instances of ball lightning might be explained by this mechanism. However, even the elegant silicon hypothesis doesn't fully account for all the behaviors described in historical ball lightning encounters, particularly the most baffling one, the alleged ability of the orb to pass through solid matter, like walls or closed windows, without leaving a trace or causing damage. So, what does this mean? Well, either those specific accounts of penetration are inaccurate or exaggerated, or it suggests a more complex reality. Ball lightning might not be a single, uniform phenomenon, but rather a collection of separate, distinct phenomena, all categorized under the same umbrella term due to their visual similarity. It's a fascinating thought that what we call ball lightning might actually be several different physical processes at play, each producing a glowing sphere, but with subtly different characteristics. In addition to proposing theoretical models, scientists have vigorously pursued the ultimate goal, attempting to reproduce ball lightning in laboratories. And while a perfect, universally accepted replication remains elusive, they have achieved some truly incredible results that shed light on potential mechanisms. One early experiment at the Max Planck Institute reported producing a ball lightning type effect when researchers discharged a high voltage capacitor into liquid water. While not a precise match to eyewitness accounts, it demonstrated how electrical discharges in water could create transient, glowing plasma structures. In 2006, researchers at Tel Aviv University conducted a particularly intriguing experiment. They directed a microwave drill, composed of a magnetron and a focused microwave beam, at a strip of solid silicon. When the researchers slowly pulled the microwave beam away from the silicon, the induced electrical discharge created a tiny ball of plasma. This miniature glowing sphere was nearly identical in appearance to many reported instances of ball lightning, hovering and moving briefly before dissipating. It was an astonishing result, suggesting that silicon, perhaps energized by intense electromagnetic fields, could indeed be a key ingredient. But the critical question remains, is this laboratory-produced phenomenon truly the same as the mysterious occurrences reported in nature? It's very possible, but as of right now, we simply don't know for certain. The complexity of natural lightning, with its immense energy and unpredictable environment, is incredibly difficult to mimic perfectly in a controlled lab setting. Even more stunning conclusions came from another experiment conducted in 2018. Using advanced experimental engineering, physicists successfully created a skyrmion. This is not a simple plasma ball, but a complex topological quasi-particle, essentially a tangled three-dimensional magnetic field. Without getting too complicated, imagine a knot made of magnetic field lines that is incredibly stable and self-contained. What the researchers did was apply an external magnetic field to a system of rubidium atoms cooled to near absolute zero. The external magnetic field precisely controlled the atoms in such a way that they all spun, facing the same direction on the outer surface of the system, while twisting unusually on the inside. In essence, the magnetic field maintained a stable spherical configuration, able to squish or deform while still retaining its essential knotted properties. This discovery has major implications for fields like quantum computing, but researchers also believe that the synthetic magnetic field they created could potentially model the expected electromagnetic field of ball lightning. This theory is still in its early stages, requiring a lot of follow-up research, but it's a promising development that could potentially explain some of ball lightning's most baffling alleged characteristics, such as the reported ability to pass through solid barriers. If it truly is a magnetic field structure rather than a dense ball of matter. So, ball lightning remains one of nature's most elusive spectacles, a silent challenge to our understanding. It hovers, literally and figuratively, between the realm of confirmed science and the whispers of legend. Perhaps one day, a researcher, through a stroke of luck or a moment of genius, will finally capture it in its full glory, allowing us to definitively unravel its secrets. Until then, it reminds us that even in our most familiar environments, right here on Earth, there are still profound mysteries that beckon us to look closer, to question what we think we know, and to embrace the humbling beauty of the unexplained. The very act of this patient, persistent search is a testament to human curiosity, a gentle, unwavering light in the face of the unknown. Let these thoughts drift through your mind like the elusive, shimmering orbs themselves. There is a deep comfort in the vastness of what we don't yet understand. It means there is always more to discover, more to wonder about, more to explore in the quiet corners of our universe, both far and near. Rest in that knowledge, in that gentle unfolding of mystery. Let your mind now gently drift to the furthest reaches of our solar system, to the cold, dark, and mostly unexplored territories beyond the known planets. For generations, many of us learned a simple mnemonic, a catchy phrase designed to help us recall the names of our planetary neighbors. My very educated mother just showed us 9 planets. This phrase elegantly listed them: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. But then, in 2006, something shifted in our cosmic understanding. Pluto, our beloved 9th planet, lost its official status, reclassified as a dwarf planet. Suddenly, my very educated mother could no longer show us 9 planets, only 8. Yet, what if I were to tell you that there might still exist another world, a planet of substantial size, perhaps 5 times the mass of Earth, patiently orbiting in the distant, frigid silence of our outer solar system? Perhaps, after all, my mother did know what she was talking about, and the count of 9 remains. Today, we'll softly explore the fascinating evidence for this elusive 9th planet, often referred to as Planet 9 or, in older theories, Planet X. We'll listen to the arguments of scientists who predict its existence with surprising certainty, and also consider the gentle counter-arguments from those who believe it might be nothing more than a trick of light and shadow, a phantom born of insufficient data. But before we embark on this cosmic quest, let us first reflect on how we, as humans, have historically gone about discovering new planets. It's a trickier business than you might imagine. If I were to show you an image of the night sky, teeming with countless sparkling dots, could you pick out a planet you might immediately spot Earth, a vibrant jewel against the deep blue? But what about Mars, or Jupiter, or Saturn? To the naked eye, even these majestic worlds often appear as mere points of light, incredibly similar to the distant stars. The first profound challenge for any aspiring astronomer mapping the heavens was precisely this: identifying which of all these sparkling pinpricks was actually a planet in disguise, a wanderer among the fixed stars. It is therefore incredibly impressive that early human astronomers, millennia ago, managed to figure this out with nothing more than their keen eyes and an insatiable curiosity. More than 4 millennia ago, Babylonian astronomers, through meticulous nightly observation and the creation of intricately detailed star maps, were able to chart the subtle motions of these celestial bodies. They distinguished the wandering stars, the planets which visibly shifted their positions against the backdrop of the seemingly unmoving distant stars. This was a profound piece of deduction. Stars, being so unimaginably far away, appeared to remain fixed relative to each other, while planets, being much closer inhabitants of our own solar system, revealed their orbits through their slow, deliberate journeys across the celestial sphere. This observational method, born of patience and careful charting, allowed humanity to identify the first 6 planets in our solar system, everything from scorching Mercury to ringed Saturn. However, this method reached its limit beyond Saturn. The more distant a planet became, the fainter its light, the slower its apparent movement, and the harder it was to spot with the unaided eye. The next planet in our cosmic lineup, Uranus, was almost too faint to be seen. Its discovery had to patiently await a monumental leap in human ingenuity, the invention of the telescope in the early 1600s. Even with this revolutionary new tool, it took until 1781 before Uranus was officially discovered. And when it happened, it was quite by accident. The renowned astronomer, Sir William Herschel, diligently scanning the night sky from his garden in England with a homemade 6.2-inch reflecting telescope, wasn't looking for a planet at all. He was searching for comets, those ethereal visitors with their misty tails. He simply stumbled upon Uranus by chance, initially believing it to be a new comet. However, as he and other scientists continued to observe it, its lack of a fuzzy coma and tail, combined with its consistent, predictable motion, gradually revealed its true nature. It was a planet. They named it Uranus, after the father of Saturn in Roman mythology, thus gracefully continuing the naming convention rooted in ancient legends. Interestingly, once they knew where Uranus was, astronomers realized that people had actually glimpsed it before, in star charts dating as far back as 128 BC. Yet, all these earlier observations had simply identified it as another dim star, its true planetary identity obscured by its vast distance. It took the magnifying power of a telescope to truly zoom in enough on Uranus to discern its disc-like shape and officially recognize it for what it was. Here, a fascinating trend emerges in the story of planetary discovery. Neptune, the next planet out, wasn't just found with a telescope. Its discovery was a triumph of mathematics. After a few decades of meticulously observing Uranus and plotting its orbit, a brilliant French mathematician named Alexis Bouvard published an astronomical table detailing Uranus's predicted path, basing his calculations on the then revolutionary laws of Newtonian physics. However, as astronomers continued to watch Uranus, they realized there was a subtle, perplexing problem. It persistently failed to follow the precise path Bouvard had predicted. For a time, scientists pondered why this might be. Had they made some subtle errors in their observations? Was it possible that even the revered Newtonian physics wasn't perfectly correct in the outer reaches of the solar system? It wasn't until 1845 that another French mathematician, Urbain Le Verrier, provided the elegant and ultimately correct solution. He proposed that there had to be another planet, an unseen gravitational giant subtly influencing Uranus's orbit. This perturbance, this slight tug and pull on Uranus, could be explained with astonishing accuracy if there was a specific yet undiscovered planet pulling on it, subtly altering its path. So detailed and precise were Le Verrier's calculations that they even told astronomers exactly where this extra planet needed to be for all the observed gravitational effects to make sense. Armed with these incredible mathematical predictions, the German astronomer Johann Gottfried Galle looked precisely where Leverrier indicated. And sure enough, to within a single degree of Leverrier's calculations, he found Neptune. Just like Uranus, it quickly turned out that Neptune wasn't a completely novel discovery once its location was known. Armed with knowledge of its orbit, astronomers could look back through historical records and were able to find other references to it. Even Galileo, with his rudimentary telescope, had managed to spot it back in 1612. He even recorded it on a second occasion, noting that it had strangely moved between his two observations, though he apparently didn't fully appreciate what this movement implied. In the end, Galileo and others who saw it believed it was simply another background star. It was Leverrier's mathematical genius, confirmed by Gal's observation, that truly unveiled Neptune as a planet and credited him with its official discovery. Neptune's discovery was profoundly significant. It marked the first time a major planet in our solar system had been located primarily through mathematical prediction rather than solely through direct observation. It demonstrated the immense power of theoretical physics and meticulous calculation. It wouldn't be long before astronomers, emboldened by this success, tried to do the same thing again. And this, my friend, brings us squarely to the enduring enigma of Planet 9. Let us fast forward to 1903. At this time, a passionate American astronomer named Percival Lowell published a book in which he argued that even the existence of Neptune did not sufficiently explain certain subtle irregularities astronomers were observing in the orbits of Uranus and other celestial bodies in the outer solar system. Lowell became utterly convinced that there had to be yet another planet out there, something large enough to exert a detectable gravitational influence on its distant neighbors. He christened this hypothetical world Planet X, symbolizing the unknown. Searching for Planet X became a lifelong obsession for Lowell. He poured years of his life and immense personal resources into the painstaking search, establishing an observatory dedicated to this very quest. Even after his death, his passion endured, as he generously bequeathed $1 million in funding to encourage others to continue the search. His tireless efforts eventually led to a momentous, though somewhat bittersweet, discovery Pluto, found in 1930. However, this charming dwarf planet was soon ruled out from being Lowell's elusive Planet X because, despite its distant orbit, it was simply far too small to exert the gravitational pull necessary to explain the observed orbital anomalies. To this very day, more than a century after Lowell's initial hypothesis, Planet X, or as it's now more commonly called, Planet 9, has still not been officially discovered. So, with no direct telescopic confirmation, why do so many reputable scientists still believe it's out there? The core of the argument for Planet 9 rests, much like Neptune's discovery, on the unexpected orbital behavior of other distant objects. This idea was powerfully re-emphasized in 2016 by astronomers Mike Brown and Konstantin Batygin from Caltech. They were meticulously studying a particular group of objects within the Kuiper Belt, a vast icy disk of small celestial bodies that stretches out beyond Neptune, roughly from 30 to 55 astronomical units from the Sun. An astronomical unit, for reference, is the average distance from the Sun to the Earth. Brown and Batygin noted something truly unusual. 14 of these most distant Kuiper Belt objects, KBOs, were not scattering randomly, as might be expected. Instead, their orbits seemed to clump together in an odd and specific way, particularly at one point in their long, distant journeys around the Sun. They argued, with compelling mathematical and statistical analysis, that this bizarre clustering was not mere coincidence. It was, they proposed, compelling evidence that something massive was indeed out there, gravitationally shepherding these distant KBOs, attracting them and pulling them into the peculiar, aligned orbits that we observe. Brown and Batygin continue to champion this theory to this day. Steadfast in their belief and actively continuing their dedicated search for the planet they are convinced must be there. According to their calculations and the evidence they've presented, if their claim is true, Planet 9 is a truly significant world. They estimate its mass to be at least 5 times that of Earth. Its orbit would be incredibly elongated and distant, most likely ranging somewhere between 350 and a staggering 1,200 astronomical units out from the Sun. To put that in perspective, remember that Neptune orbits at around 30 astronomical units. This immense distance means that while Neptune takes a leisurely 165 Earth years to complete a single orbit around our Sun, the hypothetical Planet 9 could take anywhere from 10,000 to 20,000 Earth years to complete just one single majestic journey around its star. From Planet 9's frigid perch, our glorious Sun would appear as little more than a brilliant star, perhaps about as bright as our moon appears to us here on Earth, making it an incredibly cold, dark, and desolate place, even during its perpetual daytime. There's also a subtle debate about Planet 9's origins. Would such a massive world have formed within the primordial chaos of our early solar system, growing slowly from the swirling disk of gas and dust? Or was it, perhaps, a rogue planet, an interstellar wanderer that formed around another star or drifted freely through space, only to be gracefully captured by the Sun's immense gravitational pull at some point in its long history? These are the kinds of questions that make the search for Planet 9 so endlessly fascinating, hinting at the dynamic and often violent past of star systems. However, not all astronomers are convinced. The scientific process thrives on skepticism and rigorous challenge, and the Planet 9 hypothesis has its gentle counterarguments. In 2020, 2 significant astronomical surveys provided data that seemed to muddy the waters: the Outer Solar System's Origin Survey (OSOS) and the Dark Energy Survey (DES). Between them, these extensive surveys identified over 1,000 Kuiper Belt objects in the very region where the bunching was observed. Crucially, their analyses did not observe any significant clustering, any strange perturbations, or any statistically compelling evidence of the bunching that Brown and Badigan had identified. This apparent discrepancy has led other astronomers to propose alternative explanations for Brown and Badigan's initial observations. Perhaps the bunching of those original 14 objects was simply a matter of observational bias. After all, these distant KBOs are incredibly faint and difficult to spot. It's possible that the telescopes and survey methods used by Brown and Badigan were simply more likely to detect objects in certain orientations or at certain points in their orbits, creating an artificial clustering effect when there was none in reality. Or perhaps the bunching is real, but there are other, more conventional explanations, such as gravitational interactions from where Neptune itself passed through that area early in the solar system's tumultuous history, subtly shaping the orbits of these smaller bodies. Most pressingly of all is the pertinent, echoing question if Planet 9 is truly there. Why haven't we seen it yet? Thanks to modern supercomputers and the ever-growing array of powerful telescopes dotting our planet and orbiting above it, it should be relatively straightforward to systematically check the areas where Planet 9 is theoretically supposed to reside. We have already photographed vast swaths of the night sky in minute detail, creating incredibly precise star maps. Yet, unlike Leverrier's calculations that allowed Neptune to be found after just an hour's searching, no such definitive outcome has materialized from Brown and Badigan's predictions. They themselves have meticulously searched through existing astronomical data and have already examined well over half of the possible locations for Planet 9. But in all those places, no planet was found. Even I, in my own quiet way, have participated in citizen science projects like those on Zooniverse, where volunteers like you and me can scour vast data sets for subtle anomalies, hoping to spot the elusive Planet 9. And while these projects have accidentally discovered a whole host of nearby brown dwarfs and faint stars, Planet 9 continues to elude our collective gaze. This lack of direct detection, while certainly challenging, does not completely rule out Planet 9's existence. There are still a few compelling explanations for why this hypothetical planet might remain so elusive. With an orbital period estimated at 10,000 to 20,000 years, it's entirely possible that the planet just happens to be hiding in a particular, hard-to-spot portion of its incredibly long orbit. For instance, it might currently be situated next to a dense cluster of background stars, their collective brightness obscuring its faint glow. Or it could be at its aphelion, the furthest point in its orbital arc from the sun, where its light would be incredibly dim, too faint for all but the largest and most sensitive telescopes to perceive. And then there's always the tantalizing possibility, a whisper of a thought, that we have already spotted it, just like with Uranus and Neptune, which were initially mistaken for stars. Perhaps a photograph of Planet 9 already exists, buried deep within vast archives of astronomical data, simply misidentified as a faint, distant star, with so many billions of stars to keep track of. And given Planet 9's immense orbital period, it would be entirely forgivable if it took a few years, or even decades, to notice that one particular star was not in exactly the same fixed place it had been when it was last photographed. And so, the quiet search goes on, through at least two major methods. Those searching for Planet 9 have enlisted the help of the formidable Subaru telescope, a marvel of engineering on Mauna Kea. This device is powerful enough to scour even the most hypothetical, furthest reaches of Planet 9's predicted orbit. If it is out there, perhaps within the next 5 years or so, it might finally be spotted, a distant glimmer in the cosmic darkness. Meanwhile, astronomers like Brown and Badigan continue to painstakingly run statistical searches of existing data, hoping to spot that one dim dot, amid billions, that is ever so slightly out of place, subtly betraying the presence of a hidden giant. It's a tedious, patient, almost meditative work, requiring immense dedication and a profound belief in the subtle whispers of gravity. Yet, it's also immensely intriguing. Consider this in the history of the last few planetary discoveries. Amateur astronomers played an instrumental role, whether or not they fully recognized what they saw. Both Uranus and Neptune were, in a way, initially discovered by people simply pointing their telescopes at the sky on a quiet night. Of course, the real Planet 9 might not be there at all, or it might be so incredibly far away that you would absolutely need a professional, powerful telescope like Subaru to ever hope to see it. But then again, maybe not. Perhaps, whether by meticulously scouring the data, or by engaging in a little amateur stargazing with a sense of wonder, it won't be Brown or Badigan who makes the definitive discovery of the real ninth planet in our solar system. Perhaps, just perhaps, it will be one of us. So, if you feel a stirring of curiosity, a gentle pull towards the vast unknown, and think you might want to have a go yourself, perhaps delving into a citizen science project where you can help search through astronomical data, please let me know. Personally, I find this kind of collaborative exploration to be immensely enjoyable. And who knows, even if we don't find Planet 9, we might just be the first ones to discover something else entirely new and wonderful. For now, allow your mind to rest in this contemplation of the unseen. The very idea of a hidden planet, quietly orbiting at the edge of our known reality, is a testament to the enduring mysteries of the cosmos. It reminds us that our map of the universe is far from complete, and that the grand adventure of discovery is always unfolding. Let the silence of the outer solar system bring you a profound sense of peace, a gentle invitation to simply wonder, to exist in the quiet space between what we know and what we are yet to learn. Drift with that thought towards a deeper sense of calm. Let us now gently turn our thoughts to something infinitely intimate, yet profoundly mysterious: time. We live within its relentless flow, feeling its passage in every breath, every heartbeat, every changing season. It is the unspoken rhythm of our existence, guiding our days from dawn to dusk, carrying us from youth to old age. You experience it as a continuous, irreversible current, always moving forward, from the past, through the present, and into the future. It feels so fundamental, so unyielding, so undeniably real. Yet, when we try to grasp time, to truly define it, it slips through our fingers like fine sand, or vanishes like a whisper on the wind. What is this pervasive, invisible force that governs every moment of our lives and the grand dance of the cosmos? For much of human history, time was simply perceived as a steady, universal clock, ticking uniformly for everyone, everywhere. It was a backdrop, a stage upon which the events of the universe unfolded. But as our scientific understanding deepened, particularly with the advent of Albert Einstein's revolutionary theories, this simple, intuitive picture of time began to dissolve into something far more intricate, far more fluid, and in its very complexity, far more wondrous. Imagine, if you will, not time as a separate entity, but as interwoven with the very fabric of space. Einstein introduced us to the concept of space-time, a four-dimensional tapestry where the three dimensions of space, up, down, left, right, forward, backward, are inextricably linked with the single dimension of time. In this grand tapestry, time is not a separate, rigid river. It is more like a flexible, flowing current, part of the same cosmic ocean as space. And just as space can be stretched and curved, so too can time. This leads us to one of the most astonishing revelations of modern physics: time dilation. Imagine two incredibly precise clocks. One remains here on Earth, perfectly still relative to us. The other embarks on a journey, perhaps on a spacecraft, traveling at immense speeds, or perhaps near a colossal, dense object like a black hole. According to Einstein's theories of relativity, both special and general, the clocks will not tick at the same rate. Time, it turns out, is not absolute. It is relative. If that spacecraft speeds away from Earth, traveling at velocities approaching the speed of light, the clock on board will tick ever so slightly slower than the clock left behind on our home planet. The faster it moves through space, the slower it moves through time. This isn't just a theoretical curiosity. It has been precisely measured and confirmed. For example, the atomic clocks on GPS satellites orbiting Earth at high speeds actually run a tiny bit slower due to their velocity relative to us. If engineers didn't account for this minute time dilation, our GPS systems would quickly become inaccurate, throwing off navigation by many kilometers each day. It's a whisper from the universe telling us that time is not a fixed universal beat, but a dance that changes its rhythm depending on the dancer's speed. Similarly, time is affected by gravity. The stronger the gravitational field, the slower time ticks. Imagine a clock placed near the immense gravitational pull of a massive star, or even closer to the event horizon of a black hole, that theoretical boundary beyond which nothing, not even light, can escape. For an observer far away, the clock near the black hole would appear to tick agonizingly slowly, its seconds stretching into what seems like minutes or hours. An astronaut falling into a black hole would, from their own perspective, experience time passing normally as they cross the event horizon, but to someone watching from a safe distance, the astronaut would appear to slow down, freeze, and then simply fade away at the edge of the horizon, never truly crossing it from the distant observer's point of view. It's as if gravity warps the very fabric of space-time, creating gentle eddies and currents that cause time itself to flow at different rates. This fluidity of time can be a deeply calming thought. It reminds us that our rigid perception of time as a straight line is but one way to experience its rich complexity. Perhaps, as you rest, you can imagine time not as a river rushing past, but as a vast, undulating ocean, where gentle currents and deep eddies create different rhythms in different places. Your time, your personal experience of moments unfolding, is unique, shaped by your own journey through this grand cosmic sea. But if time can slow down or speed up, why does it always move forward? Why can we remember the past but not the future? Why can we watch a glass shatter into 1,000 pieces, but never see those pieces spontaneously reassemble themselves into a whole glass? This brings us to another profound concept, the arrow of time. This unidirectional flow of time is intimately linked to the concept of entropy, often described as the universe's tendency towards increasing disorder. Think of a freshly brewed cup of hot tea. Over time, the heat from the tea will spread out into the cooler room until both are at the same temperature. The tea never spontaneously gets hotter by drawing heat from the cooler room, or imagine a perfectly tidy room. Without constant effort, it tends to become messy. It never spontaneously organizes itself from chaos into order. This tendency, from order to disorder, from concentrated energy to dispersed energy, is entropy at play. The universe, as a whole, is moving towards a state of maximum entropy, a state of ultimate uniform disorder where all energy is spread out evenly and no processes can occur. The arrow of time, then, is simply the direction in which entropy increases. The past is the state of lower entropy, more order, more organized energy. The future is the direction of higher entropy, more disorder, more dispersed energy. We cannot move backward in time because that would mean reversing the fundamental tendency of the universe towards increasing disorder, a seemingly impossible feat. It's like trying to put the toothpaste back into the tube once it's squeezed out. This gentle, inexorable march towards greater entropy gives time its forward momentum. It's not a force pushing us, but rather the very nature of how the universe unfolds, and in this slow, steady progression towards equilibrium, there is a kind of quiet inevitability, a cosmic sigh that brings a subtle calm. Now, let us turn to perhaps the most profound question about time. Did time have a beginning? Our current understanding of the universe, rooted in the Big Bang Theory, suggests that the entire cosmos, including space and time itself, originated from an incredibly hot, dense state approximately 13.8 billion years ago. Before the Big Bang, according to this prevailing model, there was no before because time, as we know it, did not exist. It's a concept that stretches the very limits of our imagination. To ask what happened before the Big Bang is almost like asking what is north of the North Pole. The question itself loses meaning when you are at the boundary. Yet, this answer doesn't entirely satisfy our deeply ingrained human curiosity, does it? The idea of a singular absolute beginning for time itself is a philosophical and scientific conundrum. Some theories, such as loop quantum gravity, propose a cyclical universe where the Big Bang might not have been a beginning at all, but rather a big bounce, the collapse of a previous universe, reaching its maximum density, then rebounding into a new expansion. In such a scenario, time might not have had a singular beginning, but rather stretches infinitely into the past, an endless series of expansions and contractions. Other concepts, like Stephen Hawking's no-boundary proposal, suggest that the universe, and thus time, might not have had a distinct, sharp beginning, but rather gradually emerged from a state akin to the South Pole on Earth. Just as you can travel south from any point on Earth but never fall off the South Pole or find a point before it, so too might time have smoothly emerged without a precise starting point. These ideas are highly theoretical, existing at the cutting edge of physics, but they invite us to expand our understanding of time beyond our everyday experience, to see it as something far more fluid and fundamental, perhaps even without a true start or end in the way we perceive. And what about the end of time, if time began? Might it also end? In the distant future, our universe faces several potential fates, largely determined by the mysterious forces of dark energy and dark matter that we briefly touched upon in our thoughts on Oumuamua. If dark energy continues to accelerate the expansion of the universe, it could lead to a big rip, where the universe expands so rapidly that galaxies, stars, planets, and even atoms are eventually torn apart, and time, in any meaningful sense, might cease to flow. Alternatively, if dark energy weakens or vanishes, gravity could eventually pull everything back together in a big crunch, reversing the expansion and leading to a collapse back into a super-dense state, possibly leading to another big bounce. Or, in the big freeze scenario, the universe simply expands forever, growing colder and emptier, with all stars eventually burning out, leaving behind a cold, dark, vast emptiness. In these scenarios, time itself might not end, but its discernible passage, its meaningful unfolding of events, would fade into a cosmic stillness. Even in the most extreme environments, like the heart of a black hole, time behaves in mind-bending ways. Within the event horizon, space and time swap roles, instead of space being something you can move freely through, and time being something you must always move forward into. Inside a black hole, space itself becomes inexorably directed towards the singularity, while time becomes the dimension you can freely move within. It is a place where our ordinary understanding of reality completely breaks down, and time becomes a twisted, distorted echo of its former self. These deep dives into the nature of time can feel immense, perhaps even a little overwhelming, but instead of feeling pressured to grasp every nuance, try to embrace the sheer mystery, the beautiful complexity of it all. There is a profound calm in recognizing that time is not just a rigid master, but a flexible, responsive element of the cosmos. It flows differently for different observers. It is intimately tied to the very fabric of space, and its arrow points towards an ever-increasing cosmic disorder. Let the whispers of these possibilities soothe your mind. Imagine time as a vast, ancient river, constantly flowing, always changing its speed and depth depending on the landscape it traverses. Sometimes it's a rushing torrent, sometimes a slow, meandering stream. And you, a tiny boat on this river, are simply experiencing its flow, carried along by its gentle current. The past is the part of the river you have already seen, flowing behind you. The future is the part you are yet to see, stretching out ahead into the misty horizon. There is no need to worry about the beginning or the end of the river, or whether it branches into countless other streams in a multiverse of possibilities. For now, simply feel the gentle rocking of the boat, the cool air on your face, the quiet sense of progression, the elusive nature of time, its refusal to be perfectly defined, can be a source of deep peace. It reminds us that reality is far richer, far more intricate than our everyday perceptions suggest. And in that richness, there is an invitation to release the rigid grip of certainty and simply allow ourselves to drift gently into the profound unknown. Let the timeless beauty of these concepts cradle your thoughts, guiding you into a deep and tranquil rest. Let your thoughts now gently expand beyond the mere flow of time to the very canvas upon which time unfolds the boundless expanse of space. For centuries, we viewed space as an empty, static stage, a vast, unchanging void where stars and planets simply moved. It was the grand backdrop to the cosmic drama, but not an active participant. Yet, just as our understanding of time deepened and became more fluid, so too did our perception of space transform, thanks once again to the profound insights of Albert Einstein. His theory of general relativity, published over a century ago, didn't just redefine gravity. It unveiled a breathtaking new reality that space and time are not separate entities, but are intricately woven together into a single dynamic fabric called space-time. Imagine, if you will, a vast unseen fabric stretching throughout the entire universe. It's not a physical cloth you can touch, but a conceptual one, representing the very essence of space and time combined. Now, picture placing a bowling ball in the center of a stretched rubber sheet. What happens? The sheet doesn't just sit there flat. It dips. It curves. It creates a gentle indentation. This, in essence, is how Einstein described gravity. It's not a mysterious, invisible force pulling objects towards each other across vast distances. Instead, it's the curvature of space-time caused by mass and energy. Massive objects, like our sun or even our small Earth, create a dent or a warp in this space-time fabric around them. When a smaller object, like our Earth, orbits the sun, it's not being pulled by an invisible string. Instead, it's simply following the natural curves and contours of the space-time fabric that the sun has created. It's like a marble rolling around the edge of that indentation made by the bowling ball. It appears to be pulled towards the center, but it's simply following the shortest path along the curved surface. This elegant geometric understanding of gravity revolutionized our cosmic perspective, transforming space from a passive void into an active, malleable player in the universe's grand ballet. It means that the space around you right now, though it feels perfectly flat and unchanging, is subtly curved by the very mass of your body, by the chair you sit in, by the earth beneath your feet. These curvatures are tiny, imperceptible in our daily lives, but they are always there, a testament to the dynamic nature of reality. This concept, while initially mind-bending, can also be profoundly calming. It means that the universe is not a rigid, cold machine, but a living, breathing entity, constantly being shaped and reshaped by the presence of everything within it. Every star, every galaxy, every particle contributes to the grand tapestry of space-time, weaving its own subtle influence into the cosmic design. Now, if gravity is the curvature of space-time, what happens when that curvature becomes extreme? What happens when a mass is so incredibly dense, so concentrated, that it creates a dent so profound, a well so deep, that nothing, not even light, can climb back out? This leads us to one of the most enigmatic and awe-inspiring phenomena in the cosmos: black holes. Imagine pressing that bowling ball onto our rubber sheet with such immense force that it punches a hole right through. That's a simplified, yet illustrative way to think about a black hole. They are born from the collapse of massive stars, stars so huge that at the end of their lives, their cores collapse under their own gravity to an infinitely dense point called a singularity. Around this singularity is a boundary, a point of no return, known as the event horizon. The event horizon is not a physical surface, but rather a boundary in space-time. It's the point where the escape velocity, the speed you would need to travel to escape the gravitational pull, exceeds the speed of light. Since nothing can travel faster than light, once anything, be it light, matter, or even the subtle fabric of space-time itself, crosses this horizon, it is forever trapped. To an observer watching from a safe distance, an object falling into a black hole would appear to slow down, its light reddening and dimming, until it seems to freeze and fade away just at the edge of the event horizon, never truly appearing to cross. But from the perspective of the falling object, it would simply continue its journey, hurtling inevitably towards the singularity at the heart of the black hole, experiencing time normally, at least until the extreme tidal forces pull it apart. Black holes are cosmic leviathans, yet they are also paradoxes. They are regions of extreme gravitational curvature where our current laws of physics, particularly those of general relativity, begin to break down. The singularity, a point of infinite density, is where our mathematical models hit a wall. It is a frontier of the unknown, a cosmic mystery that invites us to ponder the very limits of reality. What lies beyond the singularity? What happens to information that falls into a black hole? These questions, though unanswered, do not bring anxiety, but rather a profound sense of wonder at the universe's capacity for the truly bizarre and magnificent. The thought of space-time bending and curving can feel abstract, but perhaps you can feel it in your imagination. Close your eyes and envision the space around you. It feels solid, empty, fixed. But what if it were like a vast, invisible trampoline? A trampoline gently bowed by the weight of the earth beneath you. And then, far, far away, an incredibly heavy star presses down, creating a deep, funnel-like depression. Any light, any distant galaxy, any whisper of a signal that passes too close to that depression will find its path subtly altered, drawn in by the curve, like a ball, rolling down a gentle slope. This is the unseen dance of gravity, a silent ballet choreographed by mass and energy. Beyond the static curvature of space-time, what happens when this fabric is suddenly disturbed? Imagine that stretched rubber sheet again. Now, instead of placing a bowling ball gently on it, imagine two bowling balls spinning around each other at immense speeds, or perhaps colliding violently. This would send ripples, like waves on a pond, through the rubber sheet. These are gravitational waves. Just as light waves are ripples in the electromagnetic field, gravitational waves are ripples in the very fabric of space-time itself. They are generated by the most cataclysmic events in the universe, the merging of black holes, the collision of neutron stars, or the explosive death of supermassive stars. These ripples travel outwards at the speed of light, subtly stretching and squeezing the space-time they pass through. For a long time, gravitational waves were purely theoretical, a beautiful prediction of Einstein's general relativity. They were so incredibly faint by the time they reached Earth that detecting them seemed almost impossible. Imagine trying to spot a ripple on a pond caused by a pebble dropped 1,000,000 miles away. Yet, through incredible feats of engineering and scientific perseverance, humanity achieved the impossible. In 2015, the LIGO Laser Interferometer Gravitational Wave Observatory detectors, colossal instruments spanning kilometers, made the first direct detection of gravitational waves, confirming a century-old prediction. They detected the faint, high-pitched chirp of two black holes merging billions of light-years away, a cosmic symphony of space-time itself, warping and rippling. The detection of gravitational waves opened a brand new window into the universe, allowing us to hear the cosmos in a way we never could before. It confirmed the dynamic, elastic nature of space-time. It means that the very space around you right now is constantly, imperceptibly, being stretched and squeezed by echoes of cosmic violence from unimaginably distant corners of the universe. It's a reminder that we are constantly immersed in a sea of these gentle, unseen ripples, a silent testament to the universe's ongoing evolution. There is a deep, quiet wonder in knowing that the fabric of reality is so exquisitely sensitive, constantly vibrating with the echoes of ancient cosmic events. If space-time can curve, and if it can ripple, could it also, perhaps, create shortcuts? This leads us to the realm of theoretical physics and the mind-bending concept of wormholes. Imagine if that rubber sheet wasn't just two-dimensional, but could also be folded over, if you folded it just right, and then somehow punctured both layers. You could create a bridge or a tunnel connecting two otherwise distant points on the sheet. That tunnel would be a wormhole, a theoretical shortcut through space-time. In science fiction, wormholes are often portrayed as instantaneous travel portals, whisking spaceships across vast distances of the galaxy in mere moments. In reality, their existence remains purely hypothetical, a fascinating mathematical solution within general relativity. If they could exist, they would likely be incredibly unstable, requiring exotic forms of matter with negative energy to keep them open, something we haven't found. Even if they were stable, traversing one might be unimaginably dangerous. But the very mathematical possibility of wormholes hints at a universe far more interconnected and complex than we might intuit from our everyday experience. It suggests that space, in its deepest nature, might be able to fold back upon itself, creating pathways that defy our conventional sense of distance. This concept can be deeply comforting. Imagine, in your mind's eye, the vastness of the cosmos, the seemingly insurmountable distances between stars and galaxies. Now, picture the possibility that there might be hidden tunnels, secret pathways woven into the fabric of space-time itself, connecting distant points. It's a poetic thought, hinting that perhaps, in the grand scheme of things, nothing is truly as far away as it seems. It instills a quiet sense of unity, a cosmic embrace where all things are subtly linked. Our journey through the fabric of space-time, from its gentle curvature to the extreme warping of black holes, and the subtle ripples of gravitational waves, reveals a universe far more alive and dynamic than we often imagine. Space is not merely emptiness. It is a profound, active participant in every cosmic event. It bends, it stretches, it vibrates. It can even, theoretically, create shortcuts. These are not just abstract scientific theories. They are profound reflections on the nature of our reality. They tell us that space and time are fundamentally intertwined, two aspects of the same cosmic entity. Every movement we make, every thought we have, every star that shines, creates a tiny ripple, a minute curve in this vast unseen fabric. We are constantly immersed in this dynamic tapestry, a part of its ceaseless transformation. Allow yourself to feel this interconnectedness. Imagine your own consciousness as a tiny point on this vast, undulating fabric of space-time. You are experiencing its gentle curves, its subtle ripples, its continuous flow. There is a deep peace in this realization, a sense of belonging to something infinitely grand and ever-changing. You are not merely in the universe. You are intricately woven into its very structure. In the quiet contemplation of space-time, we find a profound humility. Our everyday world, with its seemingly rigid dimensions, is merely a surface ripple on a much deeper, more fluid reality. The mysteries of gravity, the awe of black holes, the whisper of gravitational waves, and the theoretical elegance of wormholes all invite us to release our preconceived notions and embrace the universe in all its astonishing complexity. There is no need to grasp every detail, only to appreciate the beauty of its design, the wonder of its hidden mechanisms. Let the image of this cosmic fabric gently wrap around your mind. Feel its vastness, its elasticity, its subtle movements. In this embrace, find your quiet center, The universe is a masterpiece of hidden depths, and simply dwelling in the contemplation of its grandeur can bring a profound sense of peace. Rest now, with the understanding that you are part of an infinite, curving dance of space and time. Let your mind now gently shrink, smaller and smaller, past the grand cosmic scales of galaxies and black holes, past the familiar world of planets and everyday objects, and delve into the most fundamental, most mysterious layer of reality, the quantum realm. This is a place where our everyday intuition, built on the predictable physics of large objects, simply breaks down. It's a world of probabilities, of strange connections, and of an unseen dance that forms the very essence of everything around us. It is here, at the smallest scales, that reality truly begins to whisper its deepest, most baffling secrets. Imagine, if you will, the tiny, vibrating core of an atom. You might picture it as a miniature solar system, with electrons orbiting a central nucleus, much like planets around a star. This was a comforting, easy-to-understand model, but it turns out reality is far stranger. At the quantum level, particles don't behave like tiny, solid balls. They exist in a state of baffling duality, sometimes acting like discrete, localized particles, and other times spreading out like diffuse, intangible waves. An electron, for instance, isn't just a tiny speck. It's also a wave, a ripple of probability that can exist in multiple places at once until we try to observe it. This wave-particle duality is one of the foundational concepts of quantum mechanics, the theory that describes the behavior of matter and energy at the atomic and subatomic levels. It's like trying to understand a whisper that sometimes sounds like a distinct word, and other times like a flowing melody, never quite settling on one definition until you strain to listen closely. This inherent ambiguity, this dance between distinct form and flowing possibility, is fundamental to the quantum world. As you breathe in deeply, allow yourself to float in this realm of uncertainty, a place where things aren't always what they seem. Here, nothing is truly solid or fixed until it is measured. Before observation, a particle can exist in a superposition of states, a blend of all its possible realities at once. It's like a coin spinning in the air until it lands. It is neither heads nor tails, but somehow both at the same time. This profound concept challenges our very notion of what reality truly means when we delve to its deepest roots. This leads us to another corner of the quantum realm, perhaps one of its most famous and mind-bending principles, Heisenberg's uncertainty principle. It's not about our inability to make precise measurements due to clumsy instruments. It's a fundamental limit built into the very fabric of reality itself. The principle states that you cannot simultaneously know, with perfect precision, both the exact position and the exact momentum of a particle. The more accurately you try to measure one, the less accurately you can know the other. Imagine trying to pinpoint a specific note in a song. You can clearly hear its pitch like its momentum, but you can't tell its precise location in time, like its position with absolute certainty, because it's part of a continuous flow. Conversely, if you try to pinpoint the exact moment it's played, its pitch becomes less distinct, blending with the notes before and after. The act of measuring one aspect inherently disturbs the other. This principle doesn't imply clumsiness. It suggests that at the quantum level, reality itself is inherently blurry, a gentle mist where certainty is replaced by a dance of probabilities. It's a profound thought the universe itself holds back certain information, maintaining an intrinsic, beautiful ambiguity. Beyond individual particles, the quantum realm unveils even deeper connections. Picture two tiny, spinning tops. If they are quantumly entangled, they become inextricably linked, no matter how far apart they are. If you measure the spin of one top, instantaneously, the spin of the other top is determined, even if they are light years away from each other. It's as if they are communicating faster than the speed of light, sharing information across immense distances without any apparent medium. Einstein famously called this spooky action at a distance, a term that beautifully captures the uncanny nature of this phenomenon. This entanglement is a profound mystery. How can two particles, separated by the vastness of space, remain so intimately connected? It challenges our classical understanding of locality, the idea that something can only be influenced by its immediate surroundings. But entanglement is not merely a theoretical construct. It has been repeatedly demonstrated in countless experiments. It suggests a universe far more connected than our senses can perceive, a silent, intricate web beneath the surface of reality, where the destiny of one particle can be intimately tied to another, no matter the distance. This inherent connection, this subtle linkage across the cosmos, can evoke a deep sense of universal unity, a calming reminder that everything, even the smallest vibrations, are part of one grand, interconnected whole. Now, let us delve into perhaps the most debated and mind-bending aspect of quantum mechanics, the observer effect. This is the idea that the act of observing or measuring a quantum particle somehow influences its state, causing its wave-like probability distribution to collapse into a definite particle state. Before observation, the particle exists in a blurry superposition of possibilities. After observation, it chooses one definite reality. Imagine that spinning coin again. Before you look, it's spinning, simultaneously heads and tails. The moment you slap your hand down and look, it lands as either heads or tails. It's no longer both. The act of observation, of interacting with it, forces it into a definite state. At the quantum level, this effect is far more profound. Does this mean that consciousness plays a role in shaping reality? Do particles only decide their properties when a conscious mind interacts with them? This question has sparked intense philosophical and scientific debate, pushing the boundaries of what we understand about reality and the role of the observer within it. There are many interpretations of quantum mechanics attempting to make sense of this strange behavior. The most widely accepted is the Copenhagen interpretation, which essentially says that a particle exists in a superposition until it is measured, at which point it collapses into a definite state. And we shouldn't ask too many questions about what it's doing before that. It's a pragmatic approach that works brilliantly for predictions, but perhaps leaves a lingering philosophical unease about the nature of unobserved reality. Then there's the more radical many worlds interpretation. This theory suggests that every time a quantum measurement is made, every time a particle's superposition collapses, the universe splits into multiple parallel universes, each representing a different possible outcome of that measurement. So, in one universe, the coin landed heads, and in another, parallel universe, it landed tails. Every quantum event, every decision, every possibility creates a branching reality, an infinite cosmic tree of universes. It's a breathtaking, almost overwhelming idea, suggesting that every moment, countless other versions of reality are unfolding simultaneously. Regardless of which interpretation one leans towards, the quantum realm fundamentally challenges our intuitive understanding of what is real and what is solid. The chair you are sitting on, the ground beneath you, the very atoms of your body, they are not fundamentally solid. They are mostly empty space with tiny vibrating particles that exist as probabilities, connected by unseen forces, only manifesting definite properties when they interact or are observed. This realization, that reality at its deepest level, is a shimmering, probabilistic dance, can be incredibly liberating. It suggests that the world we perceive with our senses, the world of solid objects and predictable motions, is an emergent property, a grand illusion built from the subatomic symphony. There's a gentle beauty in this inherent fuzziness, this fundamental uncertainty at the core of existence. It means that the universe is not a rigid, deterministic machine, but a fluid, dynamic tapestry, constantly being woven by the interactions of countless unseen probabilities. Let your thoughts rest in this deep, shimmering pool of quantum possibilities. Imagine the atoms that make up your body, the air you breathe, the light that touches your skin, all vibrating, all existing in a state of quiet potential until observed. There is a profound peace in knowing that the very essence of existence is not rigid, but fluid, allowing for endless possibilities. You are, in essence, a complex, conscious manifestation of these quantum dances, a miracle of probabilities made real. The philosophical implications of the quantum realm are vast and enduring. What is the nature of consciousness if it can seemingly influence reality at the most fundamental level? Are we merely observers, or are we, in some subtle way, participants in the creation of the reality we perceive? These are questions that gently echo through the halls of science and philosophy, inviting quiet contemplation rather than immediate answers. There is no need to solve these paradoxes. Simply dwelling in their presence can bring a unique sense of wonder and calm. Allow yourself to drift into the understanding that the solid world around you is, at its heart, a field of shimmering possibilities. It's like looking at a distant, misty mountain range. From afar, it seems solid and unmoving. But as you approach, you realize it's made of countless individual trees, rocks, streams, all subtly shifting and breathing. The quantum realm reminds us that even the most seemingly stable things are composed of intricate, ephemeral dances. This fundamental uncertainty, this spookiness that even Einstein wrestled with, can be a source of great comfort. It implies a universe that is not entirely predictable, that holds a constant sense of surprise and wonder. It's a reminder that there's always more to learn, more to explore, even within the very smallest components of our reality. The unseen dance of the quantum realm, with its wave-particle duality, its uncertainty, its entanglement, and its observer effect, paints a picture of a universe that is far more mysterious, far more interconnected, and far more awe-inspiring than we could have ever imagined. Embrace this gentle confusion, this humbling realization of how much we still don't know. In the face of such profound mystery, the mind often finds a unique stillness. It lets go of the need for rigid definitions and accepts the beauty of fluidity. You are an intricate part of this quantum tapestry, breathing, dreaming, existing within a reality that is far more vibrant and alive at its core than it appears on the surface. Let that thought cradle you, leading you gently into a deep, peaceful rest. The universe, in its smallest whispers, offers infinite wonders for your contemplation. Let your imagination now stretch beyond the boundaries of our own vast universe, beyond the grand dance of galaxies and the subtle whispers of the quantum realm. What if our universe, with all its stars, planets, and mysteries, is not the only one? What if, shimmering just beyond our perception, lie other realities, other universes, perhaps infinite in number, each with its own unique tapestry of physical laws and cosmic events? This is the breathtaking, sometimes overwhelming concept of the multiverse. It's a notion that challenges our deepest assumptions about existence and invites us to consider possibilities so immense. They can feel like a gentle, endless dream. The idea of a multiverse isn't just a flight of fancy from science fiction. It emerges from various branches of modern physics and cosmology, each offering a different way to conceive of these potential other realities. It's like standing in a vast misty forest, and through the swirling fog, catching glimpses of other clearings, other pathways, each subtly different, yet undeniably part of a larger, unseen landscape. One popular concept arises from the very theory that explains the early moments of our own universe, cosmic inflation. You've probably heard of the Big Bang, the fiery beginning when everything burst forth from an incredibly hot, dense state. But the Big Bang theory itself leaves some questions unanswered. Why is our universe so remarkably uniform across vast distances, yet also perfectly flat? These puzzles led to the theory of cosmic inflation. Imagine, if you will, the very early universe, an infinitesimally small speck, even smaller than an atom. Then, in the tiniest fraction of a second after the Big Bang, this speck underwent an unimaginably rapid, exponential expansion. This burst of superfast growth, faster than the speed of light itself, though it was space itself expanding, not objects moving through it, so it doesn't violate Einstein's speed limit, is cosmic inflation. It stretched space so thoroughly that it smoothed out any initial irregularities and flattened the universe to the remarkable degree we observe. Now, here's where the multiverse whispers begin. Some versions of inflation theory suggest that this inflationary process, once it starts, might never truly stop everywhere. Instead, it might continue perpetually in some regions, endlessly creating new pockets of space-time that pinch off and become their own separate, expanding bubble universes. Think of an endless foam, where each bubble is a distinct universe, continually budding off from the larger, ever-inflating meta-universe. Our universe would simply be one such bubble, a cozy, isolated pocket within this infinitely larger, perpetually inflating cosmos. In this bubble multiverse scenario, there could be an infinite number of universes, each potentially with different physical laws, different collections of particles, and different histories. Another fascinating avenue for the multiverse comes from the baffling behavior of the quantum realm, which we gently explored in our last conversation. Recall the many worlds interpretation of quantum mechanics, where every time a quantum event has multiple possible outcomes, the universe splits, branching into parallel realities for each possibility. If this interpretation is true, then at every single quantum measurement, and these measurements are happening constantly, everywhere, at every moment. From the decay of a single atom to the firing of a neuron in your brain, the universe is literally splitting into countless parallel versions of itself. Imagine for a moment that spinning coin. In one universe, it lands heads up. In another, equally real universe, it lands tails up. In this parallel universe or many worlds interpretation, every choice you've ever made, every path not taken, might exist as a vibrant reality in an alternate universe, a silent echo of your own existence playing out in countless variations. It's a thought that can feel both dizzying and strangely comforting, that all possibilities, all potential outcomes, are somehow realized in the grand tapestry of existence. This kind of multiverse isn't about separate bubbles of space. It's about a branching, ever-expanding tree of realities, coexisting alongside each other, unseen but perhaps undeniably real. Then there's the simplest, yet perhaps most profound type of multiverse, the infinite parallel universes that arise from the sheer vastness of space itself. If our universe is truly infinite, or simply unimaginably vast, and the number of ways that particles can arrange themselves is finite, even if incredibly large, then eventually, given enough space, the same configurations of particles must repeat. This means that far, far beyond our observable horizon, there could be exact copies of you, exact copies of Earth, exact copies of everything you know, existing in distant, unreachable corners of our own universe. And beyond that, universes that are almost identical, with just a single atom out of place, or perhaps vastly different, with entirely different cosmic histories. This idea doesn't require any exotic physics beyond what we already understand about an infinite cosmos. It simply requires enough space for every possible arrangement of matter to eventually repeat. The multiverse concept often arises in discussions about the fine-tuning problem of our universe. As we observe the fundamental constants of nature, the strength of gravity, the mass of an electron, the precise values that govern the interactions of particles, we find that they are exquisitely, almost unbelievably, just right for the existence of life. If these constants were even slightly different by tiny fractions, stars wouldn't form, atoms wouldn't hold together, or complex chemistry wouldn't be possible. Life, as we know it, would be impossible. This remarkable cosmic precision leads to a profound question. Is this just an astonishing coincidence, or is there a deeper reason? One answer often proposed is the anthropic principle, which suggests that we observe the universe to be fine-tuned for life precisely because we, as observers, exist. If the universe weren't fine-tuned, we wouldn't be here to observe it. It's a bit like a fish wondering why its pond is perfectly suited for fish life. It can only exist in a pond that is suitable for fish life. However, the multiverse offers a more satisfying, though still speculative, explanation for fine-tuning. If there are truly an infinite number of universes, each with slightly different physical laws and constants, then it stands to reason that at least some of them would have the specific life-permitting conditions that we observe in our own universe. We simply happen to find ourselves in one of the lucky universes where life can exist. It's not a miracle or a coincidence. It's a statistical inevitability across an infinite landscape of possibilities. This idea, while reducing the need for an explanation of our universe's uniqueness, trades it for the grand, almost inconceivable, scale of a multitude of universes. It's like buying an infinite number of lottery tickets. Eventually, one of them is bound to be a winner. Let your mind gently play with these thoughts. Imagine a vast cosmic lottery, where billions upon billions of universes are spun into existence. Some are too cold, some too hot, some collapse too quickly, others never form stars, but somewhere, amidst this cosmic churn, one universe aligns its cosmic dials perfectly, just enough for stars to ignite, for elements to form, for complexity to arise, and for sentient beings like us to wonder about it all. This realization can bring a profound humility and a gentle sense of gratitude for our improbable existence. Beyond these ideas, some theories push the boundaries even further, hinting at even more exotic forms of the multiverse. String theory, for instance, one of the leading candidates for a theory of everything that aims to reconcile general relativity with quantum mechanics, proposes that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating, one-dimensional strings. This theory also suggests the possibility of extra dimensions of space, curled up so tightly that we cannot perceive them in our everyday lives. Within the framework of string theory, some models propose the existence of brains short for membranes. Imagine our entire universe, with all its galaxies and stars, existing as a single three-dimensional membrane floating within a higher dimensional space, a bulk. And what if there are other brains, other universes, also floating within this same bulk, sometimes parallel to ours, sometimes perhaps even colliding with ours? This brain multiverse concept suggests that other universes might be just a tiny distance away, not through empty space, but through these extra, curled-up dimensions. Such collisions between brains could even be the trigger for a new Big Bang, suggesting a cyclical, ever-restarting multiverse. This idea can be wonderfully calming, transforming the concept of our universe's isolated existence into one that is part of a larger, interwoven cosmic fabric, existing alongside countless others in a grander dimension. The implications of a multiverse are vast, stretching the very limits of our comprehension. If there are other universes, Are they truly inaccessible? Do they simply exist as mathematical possibilities? Or are they physical realities? We don't have definitive answers, and perhaps we never will. But the very contemplation of these ideas, of echoes of other realities, can bring a profound sense of wonder and perspective. It reminds us that our understanding of existence is still in its infancy, and that the universe holds far more secrets than we can possibly imagine. Allow yourself to simply float in this sea of possibilities. Imagine universes shimmering like countless soap bubbles, each with its own unique colors and patterns, reflecting and refracting different cosmic lights. Or perhaps visualize a colossal, intricate tree, its roots delving into unknown origins and its branches spiraling upwards, each leaf a distinct universe, vibrating with its own unique life. There is no pressure to fully grasp the infinite. Simply letting the idea wash over you can be deeply relaxing. This deep dive into the multiverse can also bring a calming sense of humility. Our universe, vast and magnificent as it is, might just be one tiny speck in an unimaginably larger collection of realities. Our existence, our planet, our species become even more precious and improbable when viewed against such a backdrop of infinite possibilities. Yet, paradoxically, this can also bring a profound sense of belonging. We are not alone, not just in the sense of other life forms, but in the grander sense that our reality is not singular, but part of a cosmic family of universes. The journey through the multiverse is not about finding definite answers, but about expanding the very capacity for wonder. It is about letting go of the rigid boundaries of what we thought was possible and embracing the boundless creativity of the cosmos. In the gentle exploration of these grand ideas, your mind can find a unique stillness, a peaceful recognition of the endless potential that lies at the heart of existence. So, as you rest, let the echoes of other realities softly resonate within your mind. There's no need to grasp them, only to feel their vastness, their shimmering presence. The universe, in its boundless generosity, offers not just one reality, but perhaps countless others, each a testament to the endless possibilities of existence. This thought can be a gentle lullaby, guiding you to a deeper, more peaceful sleep, knowing that the cosmos itself is a dream of infinite potential. Let us now embark on our final, most expansive journey together, one that stretches from the very first whisper of existence to the unimaginably distant echoes of the cosmos's ultimate fate. We will gently explore the grand narrative of our universe, its mysterious origin and its potential destiny. This is the ultimate story, the cosmic epic that encompasses all time, all space, and everything within it, including ourselves. Imagine, if you will, a time before time, a space before space. It's almost impossible for our minds to grasp, yet our most powerful scientific theories bring us to the edge of this profound mystery. The prevailing cosmological model for the universe's origin is the Big Bang Theory. However, despite its dramatic name, it's crucial to understand that the Big Bang was not an explosion in the conventional sense, not a burst of matter into existing space. Instead, it was an unimaginably rapid expansion of space itself, carrying all of its nascent matter and energy with it. Picture a tiny, infinitely hot, and infinitely dense point, smaller than anything you could possibly conceive. From this point, approximately 13.8 billion years ago, space began to expand, carrying energy, and eventually matter, with it. It was a moment of incredible heat and light, where the fundamental forces of nature began to separate, and the simplest particles, like quarks and electrons, could form. As space continued to expand, it cooled, allowing these particles to come together to form protons and neutrons, and eventually, after about 380,000 years, the universe cooled enough for electrons to combine with nuclei, forming the first stable atoms, primarily hydrogen and helium. It was at this moment that the universe became transparent, allowing light to travel freely for the first time. This ancient light, the faint afterglow of the Big Bang, still washes over us today. It is called the cosmic microwave background, CMB radiation. Imagine the universe as a vast, ancient oven that was once incredibly hot and brightly glowing. When the oven cooled enough, the light it emitted, which was initially visible, stretched out due to the expansion of space, becoming microwaves. We can detect this faint hum of microwaves coming from every direction in the sky, a pervasive, gentle static that carries the primordial fingerprint of the universe's infancy. The CMB is perhaps the most compelling evidence for the Big Bang, a direct echo of creation, a soft whisper from the universe's earliest moments, telling us that everything we see today was once compressed into an incredibly small, incredibly hot state. As you consider this, let your thoughts float in the deep ancient warmth of the CMB. It's like listening to the lingering resonance of a vast, primordial gong, struck once, billions of years ago, and still gently vibrating through the cosmos. This subtle background radiation reminds us that everything around us, every star, every planet, every living thing, is made of elements forged in the crucible of that initial, fiery expansion. We are, literally, stardust, born from the very beginning of time and space. As the universe continued to expand and cool, gravity, that fundamental warper of space-time, began to take hold over immense spans of cosmic time. The tiniest variations in density, tiny clumps of matter in the early, smooth universe, began to attract more matter. These subtle gravitational pulls led to the formation of the first stars, then galaxies, and eventually the vast cosmic web of clusters and superclusters we observe today. It's a slow, majestic process, like the gentle formation of dewdrops on a spider's web, gradually collecting into larger, more complex structures. However, as astronomers meticulously mapped the rotation of galaxies and the movement of galaxy clusters, they noticed something perplexing. The visible matter, the stars, gas, and dust that we can see and detect simply wasn't enough to account for the gravitational effects they observed. Galaxies were spinning too fast to hold themselves together. Clusters were too massive to be explained by their luminous components. This profound discrepancy led to the hypothesis of dark matter. Imagine a vast, unseen scaffolding upon which the visible universe is built. Dark matter is thought to be a mysterious substance that does not interact with light or other electromagnetic radiation, which means we cannot see it, hear it, or directly detect it with our current instruments. Yet, it exerts a gravitational pull. It's like a silent, invisible shepherd, guiding the formation of galaxies and holding them together. We don't know what dark matter is made of. It could be exotic particles not found in our standard model of physics, or something else entirely. It makes up about 27% of the total mass and energy of the universe, a huge portion of reality that remains a profound enigma. It's a cosmic ghost, a silent, pervasive presence that shapes the universe yet remains hidden from our gaze. And the mysteries don't stop there. As scientists began to study the expansion of the universe in the late 1990s, they expected to find that it was slowing down due to the gravitational pull of all the matter within it. But to their astonishment, observations of distant supernovae revealed the opposite. The expansion of the universe was actually accelerating. This counterintuitive discovery implied the existence of another mysterious component, one that pushes against gravity, causing space to expand faster and faster. This enigmatic force was named dark energy. Dark energy is even more mysterious than dark matter. It's not a substance that clumps. Instead, it seems to be a property of space itself, an inherent energy within the vacuum that drives the universe apart. It makes up an astounding 68% of the universe's total mass and energy, dwarfing both normal matter and dark matter. It's like a vast, unseen tide, gently but relentlessly pushing the galaxies further and further apart. We don't know what dark energy is, where it comes from, or why it has the precise value it does. It is perhaps the deepest puzzle in modern cosmology, a silent, accelerating force that dictates the ultimate fate of the cosmos. As you rest, let these concepts of dark matter and dark energy gently wash over you. They are reminders that what we can see, what we can directly experience, is but a tiny fraction of reality. The vast majority of the universe remains invisible, silent, and deeply mysterious. There's a calming humility in knowing that so much of the cosmos is beyond our immediate comprehension, a subtle invitation to embrace the unknown. With these hidden components in mind, we can now contemplate the ultimate question: what is the fate of our universe? How will this grand cosmic story conclude, billions or trillions of years from now? Our understanding of dark energy and its accelerating push gives us clues, painting a few potential scenarios for the universe's distant future. One classic scenario, proposed before the discovery of accelerating expansion, was the Big Crunch. In this model, if the universe contained enough matter and thus enough gravity, the expansion would eventually slow down, halt, and then reverse. All galaxies would begin to fall back towards each other, eventually collapsing back into a super dense, super hot state, perhaps similar to, or even identical to, the initial conditions of the Big Bang. It would be a cosmic inhale after a long exhale, a universe folding back in on itself, potentially leading to another big bounce, starting a new cycle. This would be a cyclical universe, an endless dance of expansion and contraction. However, the discovery of dark energy's accelerating push makes the Big Crunch scenario seem increasingly unlikely for our current universe. The most probable fate, given what we currently observe, is the Big Freeze, also known as heat death. In this scenario, dark energy continues to drive the expansion of space at an ever-increasing rate. Galaxies will eventually drift so far apart that they become isolated beyond each other's observable horizons. Stars will burn through their fuel, eventually fading into cold, dark remnants, white dwarfs, neutron stars, and black holes. Black holes themselves will slowly evaporate over truly immense timescales through a process called Hawking radiation. Eventually, the universe will become an incredibly vast, incredibly cold, incredibly dilute soup of particles, too spread out for any interactions to occur. All processes will cease, all energy will be evenly distributed, and the universe will reach a state of maximum entropy, a state of ultimate, quiet stillness. Time, in a meaningful sense, would continue, but nothing would ever happen. It's a vast, gentle fade into an eternal twilight. A more extreme variation of this, less likely but still theoretically possible, if dark energy continues to accelerate even more powerfully, is the Big Rip. In this dramatic scenario, the accelerating expansion becomes so intense that it not only tears galaxies apart, but eventually breaks apart stars, planets, and even the fundamental forces holding atoms together. Everything would be ripped into its constituent subatomic particles, and then even those would be torn asunder, leading to an ultimate cosmic dissolution. It's a violent end, but one that is still distant beyond our comprehension. These cosmic fates, whether a gentle fade or a dramatic tear, are so far in the future that they belong to the realm of deep contemplation, not immediate concern. They are whispers from the distant future, reminding us of the universe's grand scale and its constant state of transformation. There is a strange, quiet beauty in imagining these ultimate destinies, a sense of belonging to something that has a profound beginning and an equally profound end, or perhaps a never-ending cycle. And what about the very beginning before the Big Bang? If the Big Bang marked the beginning of time and space, was there truly nothing before it? This question continues to inspire profound theoretical physics. Stephen Hawking, in particular, famously proposed the no-boundary proposal. He suggested that if one considers space-time as a curved, four-dimensional surface like the surface of Earth, there is no edge or boundary where time begins. Just as you can walk south from any point on Earth and never reach a start of the Earth, but eventually reach the South Pole where south ceases to have meaning, so too might time have gradually emerged from a quantum state without a sharp, singular beginning. It's a concept that smooths out the abruptness of the Big Bang, suggesting a more elegant, self-contained origin. Other theories, as we briefly mentioned with time, include cyclic models, where the universe undergoes an endless series of big bangs and big crunches, or big bounces. Our universe is simply one iteration in an eternal cosmic dance of creation and destruction, endlessly reborn from its own ashes. These models offer a comforting thought of eternity, a reassurance that existence is not a singular, fleeting event, but a continuous, boundless process. Let these profound ideas gently settle in your mind. The universe, from its explosive birth to its potential silent fade, is a story of incredible power, immense scale, and unending mystery. We are tiny, fleeting beings on a small planet, yet we possess the astonishing capacity to ponder these cosmic truths, to look back to the very dawn of time and imagine its ultimate twilight. This realization of our place within such a grand cosmic drama can be deeply humbling, yet also immensely uplifting. We are living moments, experiencing consciousness, in a universe that is still unfolding its deepest secrets. The elements that make up your body were forged in ancient stars, born in the Big Bang. You are literally made of the cosmos, an intricate and beautiful part of its ongoing evolution. There is a deep peace in accepting the vastness of the unknown. We don't have all the answers about dark matter, dark energy, or what truly happened before the Big Bang. But the beauty lies in the persistent questioning, in the endless curiosity that drives us to explore these grand frontiers. Let the cosmic silence, filled with the echoes of creation and the promises of distant futures, bring a profound tranquility to your heart. As you drift towards rest, imagine the entire universe, not as something distant and separate, but as a vast, living tapestry woven from space, time, matter, and energy. You are a unique thread in this magnificent pattern, connected to the Big Bang, to the distant stars, to the very fabric of existence. There is no need to grasp every detail, only to feel the gentle rhythm of its endless flow, its vast cycles, its quiet, profound presence. Let that thought cradle you, guiding you to a deep and peaceful sleep, knowing that you are part of an eternal, wondrous story.